Welcome everyone to this webinar of the IMIT project about solid-state batteries, manufacturing for the future. We are very happy to be your host today in CIC energiGUNE, your virtual host. We expect more than 300 attendees, so we think that this event is going to be a huge success. We would like to thank all the top invited speakers of today, especially, well, Michel Armand, who will be our last or even last speaker. I would like also to thank the IMIT Project Consortium for giving us the chance to hold this webinar today. And also, I would like to thank to all the people of CIC energiGUNE who have made this possible, especially the people who are in the backstage, Begoña Ortiz de la Tierra and her team, and also Estíbaliz Crespo. You will see who are the hosts of today. I will present you Roberto Pacios, that is the technology coordinator of the electrochemical storage area of CIC energiGUNE, and Raquel Ferret, who will be your first host for today. Once again, thank you very much for being there. I hope you enjoy this webinar, and well, let's start.
Good afternoon to everyone. Pleasure for me to lead this webinar of IMIT Project in collaboration with my colleague, Roberto Pacios. Before to start, I would like to remind you two important rules during the event. The first is that you know that the microphones will be muted during the event, and the second one is that participants will be able to leave their questions to the speakers in the chat, which will be answered at the end of each presentation. If due to the time some of the questions are not answered, we will make our best effort to answer them and send the answers via email. Right, let's start with the first talk. Let me introduce to our first speaker, who is engineer Wolfgang Novak. He has more than 20 years of experience in the automotive industry, with technical expertise in control units for injection systems, in electronics development, battery development, from the concept development to the start of production, in process development also, especially in automotive. At the present, he is the skilled team leader, system engineering and cell technology at battery development in AVL company. In fact, Wolfgang is the coordinator of IMIT project. Let's see the first video and start with the first talk.
Dear ladies and gentlemen, let me give you a warm welcome to this webinar. I have prepared for you a short presentation dealing with the challenges and drawbacks that the automotive industry is facing today. But first, let me introduce myself and also my company AVL in a few words. My name is Wolfgang Novak, and I'm responsible for the systems engineering and cell technology skill team in the battery development of AVL, located in the headquarters in Graz, Austria. A few words about AVL. AVL is the largest independent technology partner for engineering services in the automotive industry. We provide innovative solutions for our customers in the development, the simulation, and the testing of powertrain systems today and in future. The company was founded in 1948, has 11,500 employees, is active in 26 countries all over the world, and has more than 70 years of experience in the automotive industry. Especially the global battery competence team is nearly spread all over the world so that we can support our customers at close range. More than 400 engineers worldwide are dealing with the development of electrical storage systems since more than 10 years for all kinds of applications, but mainly focused on automotive applications, from two-wheelers to passenger cars and also commercial vehicles. We can provide all the competencies that you need during a series development process of a battery system. Starting from benchmarking and battery cell research topics, the concept development in an early stage, different module and pack simulations, series development, including also battery management systems, and prototype build-up, as well as series production and cost engineering are in the portfolio. That means we are possible to deliver all elements from scratch to start of production for your battery system. So now let's come back to the topic of today. So what are the challenges and drawbacks that the automotive industry has to face in the 21st century? Of course, nearly everything is driven by the climatic goal. So I want to focus on the pathways to a clean and sustainable propulsion system that enables individual mobility in the future. In the terms of climatic and environmental goals, it is also important how we recycle and reuse the raw materials that are available only in a limited amount on our planet Earth. That is the reason why a second life and recycling of the components will play an important role in the future. The battery means always a challenge due to the complexity of the system and the many disciplines that are involved. So I would like to point out what are the main topics there and what is the technical challenge in the implementation of an all-solid-state battery into an automotive application battery pack. At least we will draw our conclusions out of all these points and sum up what seems to be the way to clean solutions in mobility in the future. The care of Earth is our most ancient and most worthy, and after all, our most pleasing responsibility. To cherish what remains of it and to foster its new renewal is our only hope. Wendell Berry, an American poet and environmental activist, wrote these lines. So we have to take care of our environment and an efficient way to use the resources of our planet. During the last decades, humanity did not really recognize this. Technical progress was identified to be responsible on all kinds of problems arising in this topic. But only technical progress can lead us the way to solve these problems. The global surface temperature for the first 5 months of the year was the second highest on record. The year 2020 is very likely to rank among the 5 warmest years and 10 warmest years on record, according to a statistic analysis by US scientists. Although the planet as a whole is warming, this isn't happening evenly. Surface temperatures are only one indicator of climatic change. Others are ocean heat, ocean acidification, sea level, seas, Arctic and Arctic Sea ice extent, and atmospheric carbon dioxide, which continues to be at the record levels. A paradigm shift has started. People are expressing their commitment to the climate goals. Fridays for Future is only one example. And also the leaders of the world take their position. It results in the biggest transformation in the history of the automotive industry. This time, it's not the lawmakers that are leading the way, it's the OEMs who understand that they are given one last chance by the people to become sustainable and clean. And of course, there are also some tax incentives and CO2 penalties involved. The OEMs are taking actions. It's not only the vehicle during the operation, no, it is also the CO2 neutrality of the production process and the supply chain that is targeted. I have only listed some examples. You can continue the list to include nearly all players on the market. The European Union has developed a program to become the first climate-neutral continent by 2050. That means a transition to a clean and affordable industry and a sustainable, resilient and smart mobility. The EU will reduce its greenhouse gas emissions by 55% until 2030. And on the right-hand picture you can see what are the single topics how to reach these goals. We mark the topics that will have the most influence on the automotive industry. That will be the emission trading in transport, CO2 emission standards for passenger cars and vans, the Renewable Energy Directive, as well as the Energy Efficiency Directive. All that will be combined with a bonus scheme where you will be rewarded for decarbonization and you will pay for carbon, as mentioned by Frans Timmermans, Executive Vice President in the EU for the European Green Deal. Starting with renewable energy, we have several pathways using existing technologies. Biofuel is a well-known pathway and we used it with a flex fuel vehicle. Power to gas or power to liquid uses methanization or Fischer-Tropsch processes to generate fuel out of green electricity and CO2. A way to store the electrical energy is to use electrolyzers to generate hydrogen. The hydrogen can be used as an energy carrier in fuel cell electric vehicles or in vehicles with internal combustion engines. Of course, the green electricity can also be used directly in the batteries of electric vehicles. With the development ongoing in the moment, we can estimate that in the next steps the range and charging times will be absolutely comparable to the times you need to fill up your fuel tank now. The most efficient usage of energy will be realized by that pathway. After showing the demands, we will have a look at different topics. How to solve the requests of the public authorities. One of the topics will be the efficient usage of the energy storage systems far after the automotive usage in their first life. Let's talk about the battery value chain. To do this, it is necessary to keep the entire life cycle of a battery in mind. It already starts with the raw materials and to choose the right chemistry. As can be seen here, it is not enough to just focus on the first life application, in this case the automotive application, but one must also consider the question of the reuse or repurpose of the battery in a second life. Such a second life application could be energy storage in a family home, or maybe in a battery farm of an energy supplier, to buffer the energy in a power grid with decentralized production. For example, alternative sources like wind turbines or photovoltaic cells. If both seems not to be feasible, the last option is the recycling of the raw materials. Large recycling facilities are established in Germany, Belgium, France, Finland, Norway and Sweden. Some work closely together with electric vehicle manufacturers. In order to stay competitive, standards that enable an automated dismantling process have to be set. Export restrictions on used batteries and the black mass are being discussed to secure access to raw materials for the European industry. If you take a look to China, China is the global leader for the recycling of battery cells and of cathode and anode material. The Ministry of Industry and Information Technology has enforced the industry to establish two types of recycling facilities. Smaller facilities for short-term storage and large facilities for long-term operation. Plant operators should use digitalization to collect and share data with manufacturers. What are the topics to be considered in the race around the recycling industry? First, the reuse of the material is important. The OEMs will be interested in the recycling of the materials because otherwise they will not have enough raw materials for the demands that will be on the market. The next question is, what will be the value for the consumer? Who will pay money and who will save it all over the value chain? We have also to consider evolving technologies. What kind of changes into the recycling concepts will be necessary if you take into account the new development results like cell-to-body or different chemistries and integration techniques? And last but not least, it will be also of interest to describe the time to market. We recognize that the OEMs have already arranged a lot of partnerships now. So let's summarize the facts on the recycling topic in a few sentences. The legal basis will be defined by the European Community. The integration of recycling in the value chain will be essential. Recycling makes most sense if it is done locally, and there will be different partnerships. In Europe, recycling companies will cooperate with the OEMs, and in China mainly with the cell suppliers. Specifications for recycled material have to be created. AVL is dealing with all that fact and is active in research as well as in real projects for customers. Reports on the actual situations are available. So we have focused on the main challenges for the transformation of automotive industry. After that discussion, let's now face the battery system and its complexity. To handle all these requirements, it's also a challenge. If we take a look at the life cycle of a battery system, there are a few main stages. In the first life, there is an application in the automotive world. When the state of health reaches between 70 and 80%, the battery is entering its second life, maybe in a battery farm for stationary applications or something else. In the end, it will be in the recycling process to bring all the raw materials back as efficient as possible. So the message is, we have questions to answer at all different stages along the battery life cycle, from producing the battery to recycling. We as AVL are involved in these activities and bring together these different worlds with our methods, testing and simulation. Integration of different disciplines into a stringent engineering product with its large variety of requirements, depending on the target markets all over the world, lead to a very high complexity that is not easy to handle. We have to deal with chemistry, electrics, electronics, thermodynamics, and of course mechanical design to achieve a product that can be used reducing CO2 and play an important role in tackling the climate change. What we see here is the development of the battery technologies during the last years. It is interesting to see how the battery systems evolved. You see that the cells go to higher energy density. The modules are going to a smaller number of larger modules, and the dedicated platform has become much easier. The design is more and more adapted to a series production process. Benchmark reports of these cars and batteries are available at AVL. Next slide, we see also a very important trend for the next years. The integration of cells into a pack without using a module structure increases efficiency tremendously. Not to forget that you have to solve some additional challenges with such a configuration, for example in safety issues. So with the usage of solid-state electrolytes, we should solve a lot of the problems that we have with conventional lithium-ion batteries. We will be able to operate the batteries at higher temperatures. We expect higher energy densities and higher power capabilities. The lifetime and cycle times will be increased, and also safety issues will not be that dangerous anymore. But there are also important factors that we have to handle. We will face challenges in the integration of the cells, as well on mechanical as on thermal side. With this technology change to all solid-state cells, we are facing some impacts on the integration strategy into a battery pack. 3 topics I would like to mention. An increased breathing behavior will challenge us in the mechanical integration, as well as the pre-compression that we have to put on the cells. And as a third point, the higher operation temperature will challenge us in terms of insulation against the passenger cabin and sensitive parts in the car. Now let's go into more detail on all the topics. On the left-hand side, you can see the difference between a charged and a discharged conventional cell with a liquid electrolyte. You can see that there is a small difference in the dimensions of around 4% due to the breathing of the cell. If you take a look on the right side of this picture, you can see that the breathing effect is much higher in a solid-state cell, also shown in this diagram. What can we do to handle this? We have to use different mechanisms, just like special compression pads, that can stand these strong volume changes in the cells. Of course, the mechanical fixation has to be strong enough to bear the pressure coming up by these breathing effects. Also, dynamical systems, mechanically or using isostatic liquid pressure, could be imagined, but seem to be much more complex. The solid structure of the electrolyte brings also some troubles ahead. Due to this mechanical structure and the surface properties of electrodes and electrolyte require a high pressure on the cell, so that the electrical contact is good enough to ensure a proper movement of the ions during the medium. But there must not be too much pressure on the materials due to their brittleness and the behavior of the material under the breathing conditions mentioned before. Microcracks could occur and damage the cell permanently. The pressure has to be applied also very homogeneous to enable particle contact with different size particles and homogeneous deposition of lithium metal during the fast charging process. This pressure also avoids dendrite growth or boundary layer detachment. Last but not least, we will compare the operating temperature windows. As you can see, the conventional cells operate in a window between -30 degrees Celsius and around 60 degrees Celsius. If you go beyond this temperature limit, you will face first an accelerated aging, and above the 120 to 130 degrees Celsius, you run into a thermal runaway. The separator is melting and the thermal event will start. For solid-state cells, the operational window is much larger, starting also at around -30 degrees, but going up to 120 degrees Celsius. The window for optimal operation is relatively large and lead also to additional engineering measures if you want to integrate the solid-state cell into an automotive application. For the fast charging process, you should reach even higher temperatures, up to 100 degrees Celsius and more. In terms of safety, you are more or less safe because the thermal event occurs at much higher temperatures and thermal runaway starts at more than 230 degrees Celsius. So if you want to integrate the solid-state cell into a module or a battery pack, you have to do something in a different way compared to a conventional cell. You have to change the mechanical system due to breathing effect, and you have to bring in the pre-compression also. In terms of safety, the integration should become more easier. The electrical system is also to be changed due to different C rates and higher power and energy parameters. The thermal system should be changed due to higher operating temperature range and insulation of the battery as mentioned before. And last but not least, the control system has to follow different algorithms for the control of a module or pack. So what can we take away as a challenge for the integration of solid-state cells into a battery? Solid-state cells offer different properties than the conventional cells do, and so we have to adapt the whole integration process into an automotive application. As we described, a lot of changes have to be kept in mind to create the optimum operational environment. As the benefit, you will have the possibility to reach very high charging rates and high energy densities. ABL is working on all the topics and active in research and application of solid-state batteries. You can find a lot of information on this technology in our standard off-the-shelf reports that are available. Thank you for your attention.
Thank you very much, Wolfgang, for your very nice presentation. We have time for a couple of questions. I'm a bit afraid of not pronouncing very well names, but even in that case, I will take the risk. The first question from the audience would like to know your opinion about if a certain degree of concentration of recycling plants in certain areas or countries could cause dumping of remaining parts.
I think that in the moment is not clear how will be the degree of recycling material that will be used for the production of new batteries. I think that will rise during the next years, and will then have go to an optimum value, but I think it's not clear where this optimum will be in the future.
Okay, thank you very much. And the second question, I think, is easier. How will you manage the different state of health batteries for second life?
So the state of health will be a very important factor for the usage of a battery in a second life. So if the state of health will drop down tremendously, then the best option will be maybe to put it into the recycling process. There will be windows in the state of health value where the batteries can be used maybe as battery storage systems for family homes or for different farms. And there will be also a very challenging factor, that is if there is a battery management system available that will be able to deal with this battery also in the second life application. And so if all the communication protocols are well known.
Thank you very much again, Wolfgang, for your answers. And if there are no more questions, we can proceed to the next talk.
Okay.
Thanks a lot.
Let's move on to the next talk entitled Solid-State Batteries from Today to the Future. Our next speaker is Felix Richter, group leader at the University of Gießen. Dr. Felix Richter is a junior research group leader in physical chemistry, material science and characterization in the group of Professor Jürgen Janet at the Center of Materials Research and the Institute of Physical Chemistry of the Justus Liebert University. He started investigating hybrid electrolytes for solid-state batteries in 2014 in the group of Professor Peter Bruce at the University of St. Andrews and the University of Oxford. In 2017, he moved to the group of Professor Jürgen Janet, and he's particularly interested in concepts that bridge the properties of inorganic materials and polymers. Currently, the Richter Working Group specializes in analyzing the fundamental transport mechanisms of ions across the interfaces of different battery components and the development of hybrid approaches for solid-state batteries. Let's move to the video to see the talk of Mr. Felix Richter.
Hello, thank you for the opportunity of presenting to you today. I hope to present to you a summary of solid-state batteries as I see the field today, and give a view of the future where possible research directions lie. First of all, of course, the lithium-ion battery, everybody is aware of how it is made up, but I would like to highlight the interfaces, which are, of course, key aspects in liquid electrolyte lithium-ion batteries as well as solid-state batteries. A value which is not always looked at so much is the internal resistance, which in commercial lithium-ion batteries typically is 30 ohm square centimeters or less, which means also that if solid-state batteries are to beat this, then the internal resistance needs to be as low or even better. There are three types of solid-state batteries. For one, the thin-film battery, but also bulk-type solid-state batteries with inorganic solid electrolytes or polymer electrolyte. And SEM images of the cross-sections of examples of each are shown here. Now, the thin-film battery uses LiPon typically as a solid electrolyte with relatively low conductivity. That's why for going to thicker films or thicker batteries with higher energy density, bulk-type solid-state batteries, we require higher ionic conductivity, and the best ionic conductivities achieved to date are with inorganic solid electrolytes such as these shown here, but also polymer electrolytes have been developed and shown to make good cycling batteries, only at higher temperature because of the lower conductivity. But which one is best? Well, we have a look at the literature and summarized data of academic literature publications here in this Ragone diagram on the left, where we plot the specific energy against the specific power of the cells. And this summarizes lots of different solid-state batteries, and some, of course, clearly excel, such as this one here in the high power performance, or this one up here in the energy density, which is even higher than the lithium-ion battery example shown here. Now, in order to reach this high power situation, the internal resistance needs to be very low, and it is no coincidence that this cell is the world record holder of the internal cell resistance at ambient temperature, with only 14 ohm square centimeters. Now, these high energy density cells up here, published by Samsung, show their best performance at 60 degrees Celsius, which is an indicator that their cell resistance still isn't quite low enough at ambient temperature to obtain the best cell performance. And this is also evident from their publication in the Nyquist plot. They show at ambient temperature more than 50 ohm square centimeters as internal cell resistance, but as you go to higher temperatures, this drops significantly to below 30 ohm square centimeters in our competitive area range. Now I would like to take you on a voyage through the solid-state battery, meaning looking at each individual point or part of the solid-state battery as we go along, because the internal cell resistance can roughly be seen as a sum of all these individual cell components for lithium transport in series. And I've highlighted these in different colors, so the color code kind of signifies whether I believe this to be more or less achieved nowadays in green, or still a big challenge in red, or achieved maybe for some systems, but not yet on a wider scale. These are highlighted in orange. First, we have a look at the separator layer between cathode and anode. And this focuses on lithium-ion conduction and the thickness. So the internal resistance value in ohm square centimeters can be calculated by the length or thickness of the solid electrolyte divided by its ionic conductivity. And if we compare several electrolytes, for example, LATP, LaZO, and the argyrodite, then we can see that the ohm square centimeter values are relatively low, all below 10 ohm square centimeters, which means that technically all of these can in principle be used for the solid electrolyte. However, the picture is quite different when we go to the cathode composite. Here we have several aspects to look at. One is the ionic conduction through the thiophosphate or solid electrolyte, and the other is the electronic conduction to the current collector for electrons transport through cathode active material or a carbon additive. In order to investigate this, Philipp Minman from our group has investigated a cathode composite between two stainless steel current collectors, which are ion blocking, and therefore solely investigate the electronic conductivity of the composite cathode. And for this, he used a transition line model to evaluate the conductivity. Similarly, he placed the cathode composite between two argyrodite pellets and then built a cell with indium-lithium electrodes in order to have an electron blocking cell, which means that only the ions transport through the cathode composite. And with this more complex transition line model, Philipp Minman was able to evaluate only the ionic conductivity of the composite cathode. And this he brought together in this diagram, which summarizes the effective ionic and electronic partial conductivities of the composite cathode. And we can see that there's an optimum value here around 40, maybe 50 volume percent of NCM, which incidentally is also the range where we obtain the best cell results in Gießen. Unsurprisingly, the ionic conductivity drops dramatically when the volume fraction of NCM is increased, and this is the biggest challenge for the composite cathode and having a low internal resistance. We can also estimate the ohm square centimeter contribution roughly using this formula, which divides the composite cathode layer thickness divided by the volume fraction of solid electrolyte, its tortuosity of ion conduction, and the conductivity of the solid electrolyte. Plotting this, we can obtain the resistance versus the solid electrolyte conductivity, which is plotted here in this diagram. And if we say 15 ohm square centimeters should be allocated to the ion conduction in the cathode composite, we see that at least 4 beta 5 millisiemens per centimeters is required for the ion conduction in the composite cathode. Now we have a look at the diffusion resistance inside the cathode active material. And here we found that comparing liquid electrolyte and solid electrolyte cells, the performance to be worse with NCM multicrystalline materials for the solid state battery. We were able to attribute this to the internal cracking of the NCM particles during cycling. With liquid electrolyte, the liquid can infiltrate the cracks, thereby maintaining contact throughout the particle and having short diffusion pathways. However, the solid electrolyte cannot infiltrate the cracks, which is why we have obtained significant cell performance loss because of the cracking and longer diffusion pathways lithium has to transport inside the cathode particle. This means that we see cathode active material development for solid-state batteries to be one of the key aspects. Next, we'll have a look at the composite cathode, in particular the cathode interfaces, so the cathode active material interface with the solid electrolyte, because this is a place where degradation often occurs. And Felix Walter looked at the cathode composite in much detail and investigated the degradation at the current collector interface, the active material solid electrolyte interface, but also the carbon solid electrolyte interface can be degraded. With TOFSIMS and XPS, he did a detailed analysis of these thiophosphate and NCM cathode composite before and after cycling. On the left panel, you can see the SIMS analysis, so the phosphate impurity highlighted in green, which are present in the thiophosphate. And in the middle, present in the thiophosphate with NCM in blue in the composite cathode before cycling. And there only little degradation can be observed. But the situation is much changed after 100 cycles, when especially at the interfaces, a lot of green highlighted areas are visible, which symbolize the phosphate. So the thiophosphate has been oxidized by the NCM cathode active material at the interfaces. And this leads to degradation of the cell performance and increase in internal resistance. And the conclusion that effective protective coatings and new mechanisms need to be developed in this direction to prevent this degradation from happening. Equally, we investigated the carbon degradation, or better, the degradation at the carbon interface, and found a method of coating the carbon with an alumina coating by ALD, and with the lithium thiophosphate Li3PS4 electrolyte, this creates an improved cell performance when using the carbon additive, and the stability during cycling is then further improved with the alumina coating on the carbon itself. So finally, we will now look at the lithium interface with the solid electrolyte. And you may know our results, especially those by Torben Krauskopf from our group, who showed that the lithium at garnet interface actually does not minimal or practically no interface resistance when this is prepared in an optimal manner. So you might wonder why I've highlighted this in red. Well, I think of the dendrite issues that are still prevail with solid electrolytes, and especially the mechanical aspects at the interface, which need to be addressed. But I will focus here on the interface resistance, which Torben Krauskopf has demonstrated in this cell setup, where he has a garnet pellet and 2 lithium electrodes, and then built this stack into this clamp here, where he was able to create specific forces on the cell stack and measure impedance at the same time. The result is shown here on the right, where with increasing force on the cell stack, the interface resistance, shown in blue, decreases continually, and it was even possible to remove this interface resistance completely when going to isostatic pressing and very high forces, which then forms a really close and well-contacted lithium interface. However, when stripping, this interface doesn't strip evenly over the entire surface. Instead, it creates pores, and there are regions which maintain in contact during stripping when comparing the SEM image after stripping to before stripping of the lithium metal. This pore formation and loss of contact is also seen in the voltage profile. As stripping time increases, more and more contact is lost, and correspondingly at a constant current, the voltage must then increase because of the interface resistance, which increases. Now, to prove that this is indeed the mechanical separation, this can be reversed by applying pressure, and we re-obtain the original low voltage for lithium stripping, and this low voltage can be maintained by having an external cell pressure on the stack. Of course, the application of an external pressure is not ideal for applications, which is why Till Fuchs in our group investigated what could happen if we include an ionic liquid interlayer between the lithium metal and the garnet. He managed to show that the stripping can be much prolonged, up to 15 milliampere hours per square centimeters, when using this ionic liquid interlayer. And just to show the comparison here, on the left, this dashed line shows the cell with ideal lithium electrodes without ionic liquid interlayer, and the green line shows how much this can be extended, the stripping can be extended before the overpotential increases. And with these results, we have a strong indication that hybrid systems will play a big role in future. In summary, we have investigated the different forms of cell deterioration that can happen in a solid-state battery, to be the interface formation at the anode, dendrite formation, contact loss, and equally fracturing of cathode and contact loss and interface formation at the cathode active material, and propose as a view to the future that polymers can play a big role at these interfaces and as binders. And this I wish to investigate with my group in the project FLIPS, where we develop polymer coatings and protective layers for solid-state batteries. And with that, I would like to thank the group of Professor Jürgen Janek and all the collaboration partners with industry and academia who we collaborated with for these results, as well as the funding bodies and projects, and of course also my team FLIPS, for which I'm currently looking for a PhD student to complete the team. And I would like to thank you for your attention and looking forward to some questions.
Thank you very much, Felix. A very nice talk, full of interesting data and helpful information. And now we have a couple of minutes for questions. In my case, I have one question. In the case of oxide electrolytes as garnet, for example, which are quite prone to show grain-to-grain boundary effects, do you have any information, or have you done any analysis on how the different processing techniques or conditions, like for example, sintering temperature and pressure, can affect the internal resistance of the cell?
Hello, yes, thank you for the question. Yes, so the grain size in particular depends strongly on the synthesis conditions of the pellet and temperatures and times for the synthesis. Typically, the grain boundaries are found to be the places where dendrites form, where lithium nucleation happens, and where dendrite initiation can occur. So it is, of course, very important to be able to tune this. We've also found that at particular points and spots on the garnet surface, lithium can really form in very rapid whisker shape and whisker growth, which indicates that exceptionally high local current densities can be made. Now, I think it's a really important, let's say, still open question, what causes these spots, what the surface is made of to cause these high current densities and make these possible. And maybe understanding this better can actually lead to a more uniform and high current density lithium plating on the surface, which would much improve lithium dendrite formation. Hopefully prevent this.
We have maybe you have 1 minute more, just if you like to give additional information about the FLIPS project, as there is someone in the audience who would like to know more about this project.
Thank you. Yes. So FLIPS is essentially the funding of my research group, which is a government funding for 5 years, which I have obtained to fund my position, and I have funding for a postdoc and 3 PhD students, 3 PhD projects, one of which is still available, and this will deal with the preparation of thiophosphate films, essentially in tape casting and optimize binder polymers and binder studies, which will help with processing of solid-state batteries and develop this in more and look at this topic of battery processing and manufacture with thiophosphate solid-state electrolytes.
Thank you very much, Felix. Thank you very much. We have more questions, but unfortunately we don't have time, so we will write them. We'll take notes of all the questions and will be answered after the webinar and will be sent to you by email.
Okay, thank you.
To the next talk.
Thank you. So, different topic for our third talk this afternoon, stationary applications, driver for technology diversification. Our speaker is Engineer Pilar González Fernández, Iberdrola's Energy Story Manager. Pilar González has been working at Iberdrola for more than 10 years, where she's currently, as I said, the head of energy storage within the Innovation, Quality and Sustainability Department. Within Iberdrola, she has developed different functions and has worked, among others, in the CEO's cabinet and in the international management of Iberdrola. She's one of the Iberdrola's leading experts in energy storage system and has been a member of the technical committee of the European Storage Association. Let's see the interesting talk of Pilar.
Everyone, today I would like to explain the role that batteries play within the power system. And before I start, I would like to give a quick overview to give you some context of what is happening to the energy sector. So in the last decade, we have seen how renewables have reduced their costs drastically so that they have now become the cheapest source of electricity almost everywhere. And now it's the turn of demand. So we are now seeing that the decarbonization of demand is possible, first in the transport sector with electric vehicles for sure, also in building space with heat pumps, and even we are seeing the decarbonization from some industrial processes. And this is an example of how the electricity mix is being decarbonized in Spain. So we have today a lot of wind, this is the green bars here, also solar and hydro, but there are some coal, CCGTs and nuclear that are producing our electricity. So today, 44% of our electricity production comes from renewables, but by 2030, there will be a massive deployment from both wind and solar, as you can see here in this chart. And this will lead to a 75% almost renewable production by that time. And because of all these renewables being in the grid, there is also a need for energy storage, and this will come in two forms. So according to the National Energy Plan, there will be more than 6 gigawatts of storage capacity deployed in our energy system, from which 3.5 will come from pumped hydro, which is long duration energy storage, and 2.5 gigawatts from battery systems. And when we see the rest of the economy, so today, more than 75% or almost 75% comes from coal, oil, and gas. And in the future, we have to flip this chart so that instead of having only 23% from final energy being produced from electricity, we should go to 75%. And this will be possible by replacing oil with electricity, and that is through electric vehicles and, in a sense, through batteries. And the heating from gas would be replaced with other forms, and the most efficient one would be heat pumps. So as we can see, the only way to decarbonize the energy sector is through electricity, and batteries play a very important role, both in the decarbonization from electricity and also in the demand side. And what is happening to the lithium-ion batteries demand? Well, this chart really explains what is happening. So we have plotted here the annual demand of batteries from 2017 to 2030. And the scale, which is the most relevant thing, is in terms of gigawatt hours per year. So it's a massive increase in electricity, in battery production. And the reason behind this demand is the blue bar here, which are electric vehicles. So it's really the transport sector that is driving the demand for lithium-ion batteries. Of course, batteries will be deployed in the grid by 2030. It's the green bars, stationary storage. Roughly will be like 10% of the capacity, the annual demand by 2030 will come from the power sector. But although it looks very small here compared to electric vehicles, it's really quite large. So what do we have in the power system in order to store electricity? So we have different technologies, and the difference between them, it's really, as you can imagine, the different performance in terms either of scale, in terms of duration, density, efficiency, degradation. But really, in terms of large amounts, in terms of moving energy from one point to another in large volumes, there are only two technologies that we can use today because of their maturity, their efficiency, and their cost today or perhaps in the next decade, like batteries. So it's pumped hydro for long duration for more than 20 hours. It's a 100-year-old technology, and it's a very efficient technology, and it can be deployed in large scales. And then we have batteries for short duration energy storage below 4 hours. Today, it's the most promising technology that we have. And it is, in fact, the quickest technology that we have in the power grid because batteries respond in less than milliseconds. So they are really the fastest technology that we have. And where do we use these batteries within the power system? Well, really, we can use them almost everywhere, from the generation side to our networks, distribution and transmission wires, and also in our customers. But in a sense, if we look closely into all these applications that I'm sure you've heard of, we can reduce all these applications into two, really. So it's really energy applications and power applications. So energy applications are the ones that demand from 2 to 4 hours. Batteries, no, we could demand longer, but batteries so far, they're only economic below these 4 hours. So that's why we have here these 2 to 4 hour batteries. And they are normally coupled with renewables, and we normally use them once per day. So we normally use this to store the electricity coming from solar plants, from PV plants, and we move part of that energy to the afternoon. So that's why we have like roughly one cycle per day. And then we have power applications. These applications will last between 30 minutes and 1 hour, normally for frequency regulation, to balance the grid in short duration time lapses. And they usually require longer or a more number of cycles per day. It's normally 3 to 5 what they actually perform. Of course, it it depends on its case and on its grid. But in a nutshell, those will be the two applications and the two kind of batteries and requirements that the power system would have for batteries. And as I was explaining before, although compared to electric vehicle demand, the demand from batteries from the stationary storage, that is from the power system, seems to be very low. If you look into the demand, the cumulative battery capacity in gigawatt hours that will be deployed globally in the power systems, it's quite, it increases quite dramatically. And, this chart also speaks by itself. It's not in thousands of gigawatt hours, it's cumulative, but it's in the hundreds, reaching almost terawatt hour scales. So it's a great increase in demand for batteries. And this is just really the beginning, because beyond 2030, the share of renewables will increase and the need for energy storage will also increase. And of course, we cannot forget that despite electric vehicles, the batteries from electric vehicles go into another sector, they will actually be linked to the power system. All these batteries are amazing. So when you add up the millions of the scale that is in terms of millions from the automotive industry, take for instance 50 million electric vehicles with a battery of 50 kilowatt hours, that takes you to an astronomical number of 750 gigawatt hours of storage capacity within those electric vehicles. So it's massive batteries that are connected to the grid. And the way they interact with the grid, so how they charge and at what power they charge, it will really affect the power system. It could be either a positive or a negative, depending on how it's charged. So in this chart that we have here, this is the electricity demand in Spain, considering, I think this is for 2040. So in black, you can see this is the 24-hour of a day, the average demand of a day, and with all these peaks in the morning and also in the evening. So this is the base load or the base demand. And in green, you can see how electric vehicles would add to that demand and how uncontrolled charging would react to it. So if we don't have a smart charging, we could end up with great peaks of demand and a lot of stress to the power grid. And of course, we don't have here vehicle to grid, but it could also help in critical events for the grid, to take the power from those batteries back into the grid. But that will come in the next models from electric vehicles. But so far, just by adjusting when and where you charge your electric vehicle, it will really be, you just avoid any risks to the power system. And let's take a look at what is happening in terms of technology. I'm sure you all know much more than energy companies do, but this is the way we simplify things. So what is happening in all these developments of batteries because of this massive demand is that we're seeing that there is an interest in energy density, to increase energy density. Also, we need to increase lifetime at the same time reducing cost. And of course, it has to be sustainable. So those are the developments that we're seeing in the battery technology. So we're seeing this move from cobalt-free almost cathodes. Of course, here we have NMC 811, but it could be NMC 9.5.5. Then there's also a move to substitute graphite with silicon anodes, which would reduce the volume and also the cost of these batteries. And then, of course, and that is in this event, we couldn't avoid speaking about solid-state electrolytes. That would take us to another level of energy density and also of safety. But we shouldn't take for granted that depending on the application, we would need different performances from batteries. So electric vehicles would really demand great energy density cells and cells that enable fast charging. E-buses, on the other hand, are more concentrated on increasing life cycles. And for us, for power, for the power grid, for utilities, for stationary storage, we need a lot of life cycles, more than electric vehicles need, because we need to charge daily. We have these daily cycles from renewables. And of course, the very important and most critical aspect of energy storage for us is safety. We are seeing that battery projects are increasing in size as we speak. So before they were just 1 or 2 containers, then it was 10 containers, and now we're seeing like massive facilities with a lot of containers, and we really need to control that safety. So what solid state batteries will enable is to help or benefit every single application with all these energy density increases, but also the safety aspects from solid state that are critical for us. And what are we doing? What is an electricity company like Iberdrola doing in terms of energy storage? Well, first of all, as a renewable developer, energy storage is key for us. In terms of long duration, of course, we are developing and we concentrate a lot in pump hydro, and we rely on pump hydro. But we're also doing a lot in batteries, because as we were seeing, the demand for batteries will only increase, and especially as the cost of batteries is coming down. So we initiated our activity with batteries some 7 years ago with our first projects in the US. First, we started with pilot projects because battery storage was not in the money. It was not economical to build storage. So that's why we started off with the network business unit, because they were allowed by regulators to deploy and to have hands-on experience with batteries. And now we have more than 9 projects in different geographies. And now it's the renewable business. As the cost has come down, we are going from pilot projects also to commercial projects in the geographies or in the markets in which energy storage is being remunerated. And now we have more than 1,500 megawatts of pipeline of batteries in different countries. Most of them are solar with 4-hour energy storage, and it's also with wind. So it's an increasing demand of energy storage in PPAs, in auctions, and well, you name it. And of course, it's not only our experience with battery vendors and with battery technology that we experience, but we also have a strong relationship with research centers and technology centers like CIC and energiGUNE in order to understand where the technology is moving to, and also in order to develop R&D projects. Then we have a close relationship also with startups. We have more than 100 companies related to storage that we have relationship with. We also have pilot projects with Second Life, speaking about that sustainability part of the battery market. And of course, we have investments in startups that are related to energy storage. One, Wallbox, is a Spanish EV charger for commercial and also for residential customers. And another way in which we are, in which we have an idea and we also try to see where the technology is moving to, is through the associations and alliances and platforms that they are, especially in the European level with the European Battery Alliance and also with the European Energy Association for Storage or the Global Battery Alliance. There are plenty of platforms because it's really complex for a company to understand all the developments that are happening and also to raise our requirements for those batteries. It's not only the electric vehicle sector, but it's also the power system that needs those batteries. So just to finalize, as we have seen, the developments from lithium-ion batteries are enabling the decarbonization, the electrification of transport. So the demand from batteries will mainly come from EVs, but batteries will also be deployed in the power system to a certain level by 2030, but beyond that, they will be deployed massively. To date, they have not been deployed more because of the capacity duration limit. It's no longer than 4 hours, and also because the cost was too high. And solid-state batteries will not only impact EVs, but also stationary storage, as they bring benefits to almost every single application. And for any energy company like Iberdrola, so our strategy goes really through deploying short-duration batteries, and we're doing that worldwide for different applications with wind and also with solar and also standalone batteries. And of course, for long duration, we cannot forget that we have this 100-year-old technology that is still evolving, and it's today so far the cheapest for long duration and for large amounts of energy storage. So thank you very much.
Thank you very much, Pilar, for giving us the point of view, the industrial point of view of a big company like Iberdrola. We have questions from the audience. The first one is from Mark Deschamps. Lithium-ion batteries' second life is often planned to be in stationary applications. Concerning the critical aspects that you have shown in your presentation, like cycle life and safety, is this still a realistic case?
So thank you very much for that question, Mark. I think really there's every single technology has a niche application. So I think for second life batteries, it's just finding the sweet spot, which would be, as you were mentioning, not needing a lot of cycles and having a short life, that is having a short revenue stream in order to align that with the cost. So yes, I think we just need to find it. So for backup, it's just great to use second life batteries because of their lower cost.
Thank you very much, Pilar. We have another question from one of our colleagues, Mikel. He says that if systems like vehicle to grid are implemented, will this impact the lifetime of EV batteries due to the additional charge and discharge cycles?
Yes, I think whenever you charge and discharge a battery, you will degrade it, that's for sure. So it's just to see if there is a trade-off. So if you gain enough benefits from using that cycle, that extra cycle. So it really depends on how you use that battery and how you use the car and how many times you use it for vehicle to grid. So you have to see it, but for just a certain amount of times, I think it's possible and it will not affect that much the battery.
Thank you again, Pilar. We have another very interesting question from Shai Osi. What do you think about the application of redox flow batteries in stationary energy storage?
So although we're concentrating a lot in lithium-ion batteries because it's the one that is more developed, every single utility, I would say, is looking into longer duration energy storage. And within those technologies that we can see there, redox flow batteries are for sure a very positive technology, and it could have a lot of potential. We just need to find the markets that will pay for those longer hours.
Thank you very much again, Pilar, for taking part in this webinar. And now we can proceed to the next talk.
Thank you. Time to talk about gigafactories in our next talk, entitled European Gigafactories and the Role of IPCIs. Our next speaker is Dr. Frederik Bolhort. He's a senior expert at TÜV Reinhardt Consulting. Since joining the digitalization of transport and electromobility division of TÜV Rheinland in 2017, he has supported public authorities in the approval, monitoring, and review of public funded research and development projects in the fields of transportation and digital database application for mobility. It's time for this next talk.
Good afternoon, everybody, and greetings from Berlin. My name is Frederik Bolhort, and I'm a senior expert at TÜV Rheinland Consulting. Before I start with today's talk about European gigafactories and the role of important projects of common European interest, the IPCIs, I'd like to say a few words about who we are and what we do. Together with our colleagues at the Technical University of Berlin and under the management of the VDI/VDET, we carry out the accompanying research on the funding measure battery cell production on behalf of the Federal Ministry for Economic Affairs and Energy here in Germany. And our mission is to support the battery industry and to maximize the impact of the battery IPCIs. So on behalf of our client, we offer support services to the battery industry with focus on the companies participating in the IPCIs in Germany, and in doing so, we support the knowledge transfer, mainly by publishing publications and organizing events and discussions. And we support the community building by developing networks or offering matchmaking. And we support the stakeholder dialogue by organizing working groups or workshops on several cross-cutting topics in the priority area of batteries. And as one of our support services for our client and the companies participating in the IPCIs, we perform data analytics in terms of analyzing, for example, the battery market development. And in doing so, we analyze the development of battery cell demand, and we monitor the production capacities announced by the cell manufacturers. So let's start with a look at forecasts for the battery cell demand and of the production capacities in Europe first. What we see right now is an ongoing momentum in the cell market, mainly driven by the significant increase in registrations of battery electric vehicles. And as you all know, despite of the contrary vehicle market development last year, which was mainly partly due to the COVID crisis, the number of electrically driven vehicles increased significantly. In fact, the European sales volume of EVs rose so sharply last year that the numbers of new registrations in China was surpassed for the first time. So depending on the market share of EVs, which is represented in the green areas in the diagram, the battery demand of the automotive industry will rise to as much as 760 gigawatt hours per year in 2030. And this is true for the very progressive scenario, the scenario in which we see a market share of xEVs of 81% in 2030. But the good news is that the production capacities are developing similarly. Although the production capacities, which are shown in the blue area in the diagram, although they are merely announcements by the cell manufacturers, even the lower range of their capacities is within the range of the demand for the very progressive market ramp up of EVs. So what can be stated here is that the cell production in Europe will be sufficient to supply the domestic market with battery cells in the coming years. So far, so good. But has the supply situation been so satisfactory in the recent years? As you all know, the answer is no. In the last decade, the global lithium-ion demand skyrocketed with an annual growth rate of 25%. The global market volume increased from less than 25 to more than 190 gigawatt hours per year between 2010 and 2019. And of these 190 gigawatt hours in 2019, less than 10 were produced in Europe. So in retrospect, it can be said that a global market developed very quickly, in which Europe had hardly any share. And it is true that there were attempts, even by a German vehicle manufacturer, to produce cells in Europe, but most of these were quickly abandoned. So to ensure that all Europeans benefit from safer transport, from cleaner vehicles and more sustainable technological solutions, the EU Commission launched the European Battery Alliance in 2017 and adopted a strategic action plan for batteries in 2018. And considering the high share of batteries in the value added of EVs and the rapidly growing battery market, Mr. Šefčovič, the EU Commission Vice President, Mr. Altmaier, the Federal Minister for Economic Affairs and Energy in Germany, and Mr. Le Maire, the French Minister of Economy and Finance, they decided to push ahead with the establishment of a European battery cell production. And as a result, in 2019, the European Commission approved under the state aid rules a first IPCI, and in the beginning of this year, a second one to support research and innovation in the common European priority area of batteries. So let's have a look at IPCIs. In general, IPCIs are transnational major projects of common European interest that make important contribution to the growth, the employment, and the competitiveness of European industry with public funding. And provided that there is such an overriding European interest and the investments that have to be made cannot be borne by the project partners alone. Large, important, highly innovative projects can be jointly funded as IPCIs by several EU member states in accordance with the European guidelines. And in this specific case, more than 50 companies will receive funding of up to 6.1 billion euros in these two IPCIs, involving private investments of up to 14 billion euros. And on the right side, on the map on the right side, the 12 participating member states are highlighted in a bluish color, and the more than 50 companies participating in the two IPCIs are marked as well. And behind their names, there's a color code, and this color code is connected to the value created by these companies. So color-coded is the value-added stage in which the respective companies will be active in the IPCIs. And as you can see, the IPCI activities are evenly distributed along the battery value chain. And from today's perspective, we expect more than 300 partnerships between industrial and scientific players. And this initiative will lead to about 30 pilot lines and will help to establish 18,000 new jobs in the member states. So, triggered by the support of the EU Commission and financially backed by many member states, a large number of companies have set out to participate in the enormously growing battery market, and they are becoming more and more. And this is what And this creates the preconditions for meeting the previously shown strong increase in cell demand in Europe through domestic production. And this also creates the basic requirements for further development. So in the coming years, production facilities will be set up, supply chains will be established, and what is even most important, experience with the mass production of lithium-ion batteries will be gained in Europe. And all these facts together create a competitive and sustainable battery cell production value chain in Europe. What is enormously important, simply because setting up a mass battery production is not trivial, not even for established players. For example, problems with the production ramp up at LG Chem's plant in Poland have caused bottlenecks not only at Audi's e-tron plant in Brussels. And yeah, this fact is even more true for the establishment not only of one production facility, but for the establishment of an entire new industry. However, the current development is very positive, and we all can currently observe how a battery ecosystem is emerging in Europe that creates the conditions for being able to sustainably produce battery cells in Europe. And this is not only true for the recent battery generations, but also for the next generation cells and cells like the solid-state batteries, which are the subjects of today's webinar. And with this statement, I would like to end my presentation and thank you very much for listening. Finally, I would like to briefly point out the possibility to keep in touch and to benefit from our activities. So please feel free to join our LinkedIn group, the European Battery Innovation Group, or sign up for our Battery IPCI newsletter. For this purpose, you can just scan those QR codes, or you can contact me. And yeah, thank you. Here are my contact details, so please feel free to contact me, and if you want to get in touch with us and to benefit from our work. Thank you.
Thank you very much, Frederick. I think everybody agrees that gigafactories are becoming a very hot topic in which everyone wants to be involved. I'm quite surprised that there are no questions from the audience in this hot topic, but in any case, the massive build-up of production capacities in Europe over the next few years that you have shown in your presentation mainly refers to factories for current lithium-ion cell technologies as NMC or LFP. Do this already include, this map you already showed in your presentation, already include capacities for the production of solid-state batteries?
Yes, thank you for this question. Indeed, the shown build-up of production capacities, they focus on lithium-ion technologies. And yeah, this is simply because, on the one hand, solid-state batteries cannot yet be mass-produced. And on the other hand, as I said, building up an entire new industry is already a very big challenge. And yeah, as mentioned before, hardly any battery cells are currently produced in Europe, and the goal is to produce more than twice of the current global production volume in Europe by the end of the decade, and that in a sustainable way. So yeah, many many experts agree on the fact that for the mass production of battery cells, it is absolutely necessary to gain experience first. And the aforementioned example of the cell factories being built up in Eastern Europe by established and therefore experienced manufacturers facing, let's say, hurdles that confront this great challenge. And yeah, from our point of view, a huge European effort is needed to build up gigafactories on a large scale, so that these gigafactories will produce enough cells to cover the enormous increase that has been shown in the presentation. And if we reach this milestone, yeah, maybe in the second half of this decade, mass production of solid-state batteries may also be possible. But yeah, consequently, it is right to think about the second step today, as in the context of this webinar. Yeah.
Thank you very much, Frederick. And what about these IPCIs that you mentioned in your presentation? Is it still possible to participate in one of these or to get a known project funded within the framework of an IPCI?
Unfortunately, no, at least not directly. This is because the projects funded within these two IPCIs, they have been proposed to the EU Commission and notified by the Commission. Like IPCIs have to be approved by the Commission under the EU state aid rules, as I said. And this is, by the way, a very time-consuming process. But however, this concerns the projects of the more than 50 companies that are funded within these two IPCIs. But as a partner of these companies, and so to speak, indirect participation in the funding measure might be possible. And as said before, we currently assume about 300 partnerships between actors from industry and science within the IPCIs. So accordingly, participation in a specific project might offer the opportunity to participate in these very important projects of common European interest. And maybe for Germany, I can say that in addition to these large funding projects within the framework of the IPCIs, there are also smaller, more strategic funding measures that aim to create or build up the battery production value chain, focusing the entire ecosystem. So yeah, interested parties are very welcome to contact me or my colleagues, and we will check what options you have there. And yeah, all others I have to refer to the respective governments of your countries. So please ask there what options these respective member states offers.
Thank you very much, Frederick, again, for the talk and for taking part in this webinar.
Well, welcome.
We can proceed to the next talk.
Okay, what I would like to do now is to invite you to visit our research center. Unfortunately, due to the situation, there will be a virtual visit anyway. Hope you enjoyed this virtual visit to CIC energiGUNE. Okay, perfect. So let's move on to our last talk before the break, talking about manufacturing. The speaker is Dr. Marc Deschamps, and his talk is Battery Manufacturing, the Challenge Toward Polymer Battery. Let me introduce Dr. Deschamps, the head of electrochemistry at Blue Solutions. Dr. Deschamps joined Bolloré at 1999. He develops and enhances the lithium methyl polymer battery for Bolloré, Batcaps, and Blue Solution, both subsidiary companies of Bolloré. In 2011, the lithium polymer battery, metal battery, entering the mobility market as the first all-solid secondary battery. Okay, let's move on to the video with the talk.
Hello, everyone. First, I would like to thank the organizers for inviting me to speak about Blue Solution and the lithium metal polymer battery. During this talk, I will quickly describe our company, our battery, our process, and our application. Blue Solution Company is an industrial specialized in the design and the production of completely solid cell and battery. We are the pioneers of solid-state battery. Blue Solution is now the only player able to roll out this proven technology on a large scale thanks to our feedback of more than 10 years. Our batteries are able to satisfy the demand of a number of markets and to respond to the two main challenges of the energy transition, the development of clean transport and the smart management of energy. The two markets we are addressing are electromobility and stationary application. We have a key market position in Europe for the development of electric buses. Our sister company Bluebus is developing and selling 12 and 6 meter electric bus, and our second sister company, Blue Storage, provides energy storage solution to meet the challenge of energy transition and energy access for all. Of course, these two sister companies are using LMP battery. Few words about history now on important dates for Blue Solution. Our previous company named Batcap was created in 2001. It was a dedicated company for the production of lithium metal polymer battery and supercapacitor. Between 2004 and 2010, we developed the Blue Car, a prototypes of electric vehicle with a partnership of Pininfarina. We also work with Gruo for the manufacture of electric buses. During this period of time, we have installed a production unit in Brittany and inaugurated the Canadian plant. In 2011, we launched Autolib in Paris, a car sharing system with Blue Car provided by LMP battery. After we launched multiple car sharing system worldwide in Lyon, Bordeaux, Indianapolis, Turin, Singapore, Los Angeles, London. We also developed stationary application in Africa. We built a factory to make 12-meter electric buses after winning a contract with RITP. Blue Solution was created in 2013. From 2018 to now, we launched a new generation of module named IT3. We signed with the Daimler Group, enabling the equipment of e-citaro buses with LMP. We increased our production capacity on both sides of Atlantic Ocean. And on the stationary side, we have an agreement with RTE regarding the Ringo project. We have two main factories for battery, one in France and the other one in Canada. We have also one factory for buses in France. For battery, the installed capacity is up to 1.5 gigawatt-hour. We have 420 employees and 48,000 square meters are dedicated for battery production and R&D. How and why is the Bolloré Group enter the battery market? In fact, by diversifying its historical business of producing thin paper and then ultra-thin plastic film, the Bolloré Group has become a producer of dielectric component for capacitor. Using this existing skill in electricity storage with film for capacitor, Blue Solution was created to design and develop a lithium metal polymer battery. Let's talk about targeted market and clients. Our most famous client is Daimler. Blue Solution batteries power Mercedes-Benz latest generation e-Citaro buses. This confirms the perfect match of LMP battery with all-electric buses. We have, of course, strong collaboration with Bluebus, who has a long-term partnership with RTP, a recognized urban mobility leader. Already 400 buses produced and used in 60 cities. Gossin selected LMP technology for its electric power tractor. You can find IPM 75T in New Zealand, Ivory Coast, and Qatar. Actia integrates the LMP battery in the brand new Denning Elements bus in Australia. On the stationary side, our major customer is RTE, a French transmission system operator with a Ringo project consisting of 30 megawatt-hour installed in southern of France, one of the largest storage systems in France and Europe. LMP is safe, robust, efficient, and sustainable. The solid electrolyte and the metallic lithium anode provide significant advantage in terms of energy density, security, and performance. The key performances of LMP are safety, no thermal runaway reaction, no leakage. Energy density is around 250 watt-hour per kilo at cell level. Thermal stability, LMP is highly stable in aggressive temperature environments, no cooling system required to manage battery temperature, high calendar life and cycle life capability. Capacity remain nearly constant all over the life. Sustainability, no cobalt, no solvent, no rare mineral, and recyclable. Today, solid-state lithium batteries are universally recognized as the future of lithium batteries. Blue Solution is the most advanced company worldwide in this technology and the first company to bring it to the market. Made up thin film using extrusion and coating techniques, this entirely solid electrochemical cell has neither liquid nor gel element and is a key component of the only commercial battery pack using a lithium metal negative electrode. LMP is the assembling of only 4 foils. On the negative side, a lithium metal foil. On the positive side, a composite electrode made of lithium iron phosphate, carbon, and electrolyte. This cathode is linked to an aluminum current collector. Between positive and negative side, the separator, a lithium salt dissolved in PO-based polymer. Now, let's have a look on the process to make cathode and electrolyte. First, we are making the cathode film. In Brittany, we are using extrusion, and in Canada, they are using coating. The French process is represented here. A twin screw extruder is used to mix the raw material and to melt the polymer. We obtain a foil after the barrel. Then this composite electrode is deposited on the aluminum collector. We have to cover the second side of the current collector with the second cathode. What we want to achieve is high active material loading, no porosity, homogeneous thickness, component homogeneity. Moving to electrolyte now. The same process is used. Extrusion. Like for cathode, we are mixing component with a twin screw extruder. Then the barrel will allow to make the electrolyte film, which is deposited directly on the cathode. Both sides are covered by electrolytes. To make this separator, we are using two different polymers, one for ionic conductivity and the other one for mechanical strength. We need to make a co-continuous and homogeneous network, the thinner possible, but with no pinhole and with homogeneous thickness. At the end, we have made what we call an half cell. Let's go to the negative side, the anode side, the lithium side. I have to mention that parts of this process are not presented here. The raw material is lithium ingots. The press extruder is used to make a film. The objective are to obtain high lithium purity with no pollution. Thickness 20 micron is the minimum we can reach today. Smooth surface and homogeneous thickness all over the ore. After the film fabrication, it is time to assemble them. Lithium anode and half cell are laminated together, then cut and stacked. The electrochemical cell is made. By adjusting the laminate number, we can adjust the capacity. Once we have cell, they are connected in series and inserted in a sealed aluminum can. Electronic board and heater are added to create the module. LFP voltage is around 3.5 volts. We are connecting 20 cells to reach 70 volts for the module. After that, we connected 6 modules in series to make a pack of 400 volts or 9 modules to make a pack of 600 volts. To summarize, at the solution, we start by transferring powder and we finish by making pack and rack at a high level of quality. It seems easy, but moving from laboratory to industrial level is a long way with many challenges. Behind LMP and the original idea of Michel Armand, there are a lot of know-how, specific tools, and patents. Today, Blue Solution continues to focus its investment on boosting its production capacities on R&D. We expect considerable investment in production capacity in Brittany and Quebec to support the expected growth in coming year. We will sustain R&D effort to maintain our major competitive edge in the future generation of solid-state battery. We have 3 main focus for the next years. On the current technology based on lithium iron phosphate and PO, the main goal is to improve energy density. We expect to have a module of 9 kWh in 2025 compared to 7 kWh now. We are also developing a new generation called Gen 4. This technology will enable high voltage material, decrease the working temperature to room temperature, enhance C rate, especially for charging. I have not the time to present our very promising result today, but you will have information at Battery Event 2021 on that subject. The third axe of our innovation concerns recycling. We are working on a circularity concept. Our objective is to reduce our consumption of natural resources and reuse recycled raw materials. We have developed a lithium metal extraction process in-house. Over 90% of metallic lithium extracted and recovered. It is protected by a French patent and an international patent is pending. A pilot line is in operation where we are now playing with parameters to define the best configuration. Our objective is to reuse lithium in our lines with the same quality as original one. With the same objective of circularity, we are currently working on the recovery of lithium salt on LFP. Next step will concern the recovery of polymer. I thank you for your kind attention.
Thank you very much, Mark, for your very interesting talk. It's somehow appealing, very appealing to see that this technology is being industrialized and that there are some vehicles already running with this technology. You made me feel very curious about one of your last slides. When do you expect to produce all solid batteries operating at room temperature? And if you can somehow elaborate on the strategies or ways you are going in that way, if you can disclose something about that.
Sorry, I did not catch you at the end. Could you repeat, please?
What kind of strategies you are using in order to get the solid state batteries operating at room temperature? If you can disclose something about the...
it's a very curious question. And of course, we are working on different strategy to decrease the working temperature. And probably we are working on the same strategy as many others. But what I can say today is we have found some solution to work at room temperature with lithium metal and to work with a high voltage cathode. So it's a very important point for us. So we are now developing that and making cycling tests. So the results are quite promising now. What I can say is there is a long road before to have a car with that kind of battery, but we will use probably the same process to produce it. So we are quite confident that we will do it, and we did not expect bad surprise.
Okay, thank you very much. Your presentation has raised a lot of interest in the audience, and we have many questions. One of them is from Felix Richter. How are dendrites prevented in these lithium metal polymer batteries?
We are playing on two sides. One side is an interface between lithium and electrolyte. So to have a good interface is very important. So you can play with different parameters to have that, but I will not give you the right one. And the other one is electrolyte. We have designed a special electrolyte to avoid dendrites. So it's the combination of interface and electrolyte to reach that point.
And now, if we move to the other side of the device, do you have any appealing results or with high voltage positive electrodes, or are you planning to introduce manganese in your cathodes, for example?
Yes, the high voltage we are now testing is a mix of manganese and iron. So it's as asked Christian, it's a LMFP. So it's an interesting material to replace lithium iron phosphates.
And now, looking at the system, how different is the thermal management system or the battery management system in your case compared with that in conventional lithium-ion batteries?
I think it's an opposite system. In our case, we need to warm the battery, so to have a working temperature between 50 to 80, depending on the application. And in the case of lithium ion, you have to cool down. So sometimes it's easier to warm than to cool. But in our case, we have to be at the right temperature every time. So it's a bit difficult for EV, but for bus, it's not a big problem.
And now, looking back at the lithium foil, I guess that the thinner the better, but is there any minimum requirement for lithium foil thickness, maybe from the stability or mechanical point of view? And what are the prospects about anode-free polymer cells?
For the minimum, it will mainly depend on the process you have. But today we are able to reach less than 30 micron, and we are progressing, I will say, every day on that. But 30 micron is quite brighter. So at a certain point, you have a difficulty to manipulate that thin foil. And concerning the anode-free lithium, one thing you have to keep in mind is if you have a lithium-free, then you have copper, and copper is maybe 20 times more dense than lithium. So if you use 10 micron copper, then it means it's like 200 micron lithium for the weight, and it also costs a bit. So you have to find the best solution. Not an easy choice.
There is also a lot of interest in our audience about recycling. You mentioned, for example, that LMP are more suitable for recycling. Could you give us some information about that? Why it is easier than in other kind of cathodes?
Today we have developed a dedicated process for lithium metal, and we are extracting lithium metal from the cell, directly lithium metal, not going back to carbonate. So we can reuse directly the lithium metal from the recycling process to the line. Of course, maybe after purification, but I think it's not possible in the case of lithium ion. So we are now working on how to recover the salt and to reuse the salt. And we are also looking at active material, but in that case, it's more to reuse the material on the process on making lithium iron phosphate. That's why we are thinking it's more convenient to recycle because we are reusing a lot of material, not just recycle and made again material from the starting point.
Thank you very much again. I think we are a bit out of time, but there is one very interesting question. What are the typical charging rates in your LMP cells?
So it's a good point. Today it's C/5 for normal charge, and tomorrow C/4, but it's I will say much more lower than a typical lithium-ion battery. So it's a drawback of lithium, and if you want to avoid also lithium downright, you have to charge at a specific rate. So of course we will work on that for the next generation, but it's important to know that today our normal charging rate is lower than lithium-ion battery.
And somehow related to this, which is the maximum aerial loading that you have achieved?
This is confidential information, sorry.
Okay, thank you very much, Mark. And
Thank you.
now we can go to the next talk, or I mean, I think now it's time for a coffee break.
Yeah, dear participant, it's time for a break. I think we are on the schedule, more or less, perhaps some minutes late, but in any case, it's time for you to take a coffee or a Coke, and remember that we restart the talks at 15:45. Thank you. Welcome again to the second part of the Image Project webinar. Hope you rest during the break. We start with our first talk after the break. Deals with the battery manufacturing challenges towards the Gen 4 and beyond. Our speaker is Dr. Steven Bisco, Chief Executive Officer and CTO of Polyplus Battery Company. Steve Bisco is an internationally recognized expert in lithium batteries and fuel cells. He has over 100 US patents, more than 200 international patents, and is author or close to 100 journal articles, as well as books, monographs, and other publications. After he's received the Bachelor of Science and PhD, he was postdoctoral fellow at the University of California before joining the staff at the Lawrence Berkeley National Laboratory. In 2013, Dr. Bisco was selected by the City of Berkeley for a Visionary Award for his work in next-generation batteries. Steve also serves on the technical advisory boards for the Conrad Foundation and CIC energiGUNE, and was awarded in 2011 by the International Battery Association Award for outstanding contribution to the development of lithium air and lithium water batteries. In May 2015, Dr. Bisco was elected a Fellow of the Electrochemical Society. Let's move to this really interesting talk.
I'm Steve Bisco. I'm the CEO and CTO of Polyplus Battery Company. And today I'd like to walk you through some of the challenges in transitioning solid electrolyte-based technologies to the commercial market. So, virtually everyone has seen announcements like this announcing the end of the internal combustion engine. And although that hasn't happened, many auto companies have taken major steps toward introducing EVs to the commercial markets. But along with these types of announcements, you've also seen such things as the GM recall over the Bolt, and that's due to a battery concern, fires. So safety becomes and has been a big part of electrification of transportation. And so now that we're pushing for even higher performance, it raises the questions, how do we develop the next generation of high energy density batteries without compromising safety and certainly without increasing cost? So many people have claimed that the future is solid state. Polyplus is certainly working in this domain as well. So what about solid state batteries? It's likely and almost certain that as we move to solid state, that will also involve a transition to metallic lithium for the negative electrode. And the reasons for that are obvious. Lithium is 4 times the volumetric capacity density of carbon, and it's more than 10 times the gravimetric capacity density of carbon. So there's a big, there's a big jump in performance if we can do this. And in fact, if this is successful, then that's kind of the end of the development of a negative electrode, right? Because lithium is as good as you can get. So as we move to the solid state, that necessarily means we're replacing liquid electrolyte with solid electrolyte. And that requires a number of kind of key metrics. We need high lithium-ion conductivity at room temperature and hopefully below. This solid electrolyte should block lithium dendrites and be either thermodynamically or kinetically stable to lithium. And you want a low-density material because otherwise this passive component will be adding a lot of weight to the cell, which you certainly do not want to do. There needs to be a roadmap for getting to very thin materials, hopefully below 20 microns, and they need to be pinhole-free so lithium does not short the cells. And obviously, ultimately, it needs to reach parity economically with lithium-ion technology. That's a big challenge. So let's look at some of the possible paths here. Clearly, polymer electrolytes are one, and these are commercial, lithium polymer batteries. It has a big advantage of being high-speed roll-to-roll manufacturing. Polycrystalline ceramics are getting a lot of attention. That's typically done through tape casting. And glasses. Of course, are also a high-speed roll-to-roll manufacturing process. Anybody carrying a smartphone has a very thin glass display, and those are produced at scale at very high volume. So what are the downsides? Well, with polymer electrolytes, they're typically limited to warm temperatures, right? The conductivities are not very good at room temperature and certainly not below. Polycrystalline ceramics have advantages electrochemically and mechanically, but this is a difficult technology to scale, and it tends to be expensive. Glasses are already scaled, so they scale similar to polymer electrolyte. So there are some big advantages to glasses. So let's first look at polycrystalline ceramics, because Polyplus works extensively in this area. We work with a material known as LATP, which is lithium aluminum titanium phosphate, which is a water-stable solid electrolyte. So we can build lithium metal electrodes, which can be fully immersed in water. And that allows us to build some very unique battery chemistries. So here you see that's a 10 amp hour negative electrode, which is enabling for a variety of lithium metal aqueous chemistries. But, you know, the core of that structure is a lithium metal electrode, which is about 3 millimeters thick. So that's 600 milliamp hours per centimeter squared. That's a lot of capacity per unit area. If we're going to take that to a rechargeable, the metrics change, the cost change, but at this capacity density, the cost of the solid electrolyte is fine, right? It's economic in this range. It will change if we start talking about rechargeables. So this is still the most expensive component of the lithium seawater battery. And the lithium seawater battery, like as I mentioned, allows us to do some remarkable things, which is to build batteries at 2,000 watt-hour per kilogram, 1,000 watt-hour per liter. Polyplus now has a pilot manufacturing line in Berkeley. We're about to launch this commercially. And we just completed deep water testing. We had our batteries at 13,000 feet in the ocean, very high pressure, but these are incompressible electrodes, and so they do not need to be protected from those high pressures. So we can do some pretty remarkable things there with the solid electrolyte-based chemistry. So on the left-hand side, you see here lithium seawater. That is about to go commercial. But a big focus of Polyplus is developing rechargeable lithium metal batteries, and that's based on glass. And so we'll get into that in a second, how we do that. If you look at lithium seawater batteries, and there aren't too, you know, we are it actually. As I mentioned, they are very high energy density, and they're very safe because they're not batteries until they're immersed in water. So in fact, on land, they're not batteries, right? So in fact, you could crush them and there's effectively nothing happens. They're also environmentally benign, so they're you know, really remarkable systems, which is why, of course, we're about to commercialize these systems. And if you look at kind of the other batteries that have been used in deep ocean, which in fact they have to be protected from pressure, so their energy densities are vastly derated. You know, of course, ours are not. They're not even close, right? So lithium seawater, as I mentioned, has already demonstrated upwards of 2,000 watt-hour per kilogram and 1,000 watt-hour per liter, and we can probably push that a bit higher. So that is going to go commercial. You see here a picture of an older pilot line we had for square form factor electrodes. We're actually now making circular electrodes, which allow us to make cylindrical batteries, right? Which we deployed mostly in the ocean and deep ocean. So let's get back to this idea of you know, which solid electrolyte we're going to choose for a particular application. So as I mentioned, in the seawater battery, we have very high capacity density. When we move to rechargeable batteries, you know, the capacity of the positive electrode is typically in the 3 to 5 milliamp hours per centimeter squared. That's a very different domain. It means that a rechargeable battery will require 3 orders of magnitude more surface area than what we're doing in, for instance, our lithium water battery. So that means that the solid electrolyte would then be 1,000 times more expensive, right? And that's, for us, I mean, that would be a showstopper, and which is why, as we moved in the development path for rechargeables, we took a different path. So if we look at just the retail pricing of ceramics that are already globally scaled, right? Alumina, pretty common material, easy to make, actually. That's about $1,000 a square meter. And here's a material that's at 40 microns. A company named energy was producing this material. At scale, they estimated they could get to $5,000 a meter squared. And we work with this LATP material. Here you see a 20 micron membrane. We typically don't work with such thin materials because the seawater batteries don't need them. They're very expensive. And so we don't see this as a path forward just because of the scaling issues, right, and the cost. And there are other issues regarding dendrites, but the cost issue is a big one. All right, so how do we choose? This is basically the two classes of material, crystalline and polycrystalline, and then non-crystalline materials. So if you look at those, and if we just say quickly look at densities of these materials, I mean, two of the materials are getting a lot of attention, of course. Well, LATP is we're using, LLZO, but look at glass. The density of glass is low. The density of glass is low, which is a good thing, right? Because you're not going to be adding significant weight to your battery. So we're focused on glass. Here you see, kind of our path forward, which is we call glass-protected lithium metal batteries. And so we'll walk through some of the history of this and then how we actually do it. Solid-state batteries have been around. Some work that came out of Oak Ridge National Lab years ago, where they actually sputter deposit the battery. So you sputter deposit LCO, sputter a glass actually, and then deposit lithium on top of it by evaporation. And remarkably, these batteries were commercialized. There are several companies that did it at a commercial spec of about 10,000 cycles at 100% DOD. So lithium metal cycles reversibly and quite well when it is matched up with a glass which has no voids or grain boundaries. So basically no place for the lithium to travel to short the battery, and these glasses are sufficiently strong to blunt lithium if it were to try to do so. So Polyplus is working extensively in glass electrolytes, and the vision is to actually make these electrolytes, not by sputter deposition, but by the same manufacturing processes that display materials are made, which is effectively melt processing, softening the glass, drawing, pulling, the way optical fibers are pulled. And I'll show you a quick kind of scenario how that can be done. These are very conductive materials, approaching 10 to the minus 3 Siemens per centimeter at room temperature. Here you can see about a 50 micron sheet of glass. This is oxide glass, but being handled very much the way you would handle a polymeric material. So they're very flexible when you get below about 100 microns thickness. And so we take advantage of that flexibility with regards to manufacturing. If you look at the price of thin glass, it's a very different world from polycrystalline materials. Gorilla Glass, just a 100-piece order, you're already down to $40 per meter squared. Willow glass, about 100 microns, is down at below $8 per meter squared. And if you go on Alibaba and look at Chinese glass suppliers, you'll see that they're even down as low as $1 per meter squared. So these are certainly scaled at the kind of price points that we're interested in for commercial batteries. The conductivity of sulfide glasses is, as I mentioned, very high. You can see here, even at minus 20 C, the conductivity is at 10 to the minus 4 Siemens per centimeter. And these materials are sufficiently hard, as I mentioned, to stop dendrites. In fact, the elastic modulus of this glass approaches that of oxide glasses. So these are strong glasses. Here you see about a 70 millimeter disc of glass that was produced for us by Schott. It's about 400 microns thick. And we also have developed a process to stabilize these glasses against dry room environments. So if you look at, for instance, the Toyota approach, where you have high surface area sulfide electrolytes, which are compressed with either anode or cathode materials, it's difficult to protect those materials against moisture because they're very high surface area. But we have ribbons of material which can be coated very simply. We use a barrier coating which is transparent to lithium but blocking to moisture. So we have that process in-house. We obviously cycle these. Most of these glasses have been cycle tested in small cells. We're getting ready to do larger cells. You can see here that after 200 cycles, the cycles basically fall right on top of one another. Here's some extended cycling of a 400 micron thick glass. You can see that it's very reversible. We don't see any evidence of dendrites. We also cycle these glasses against NMC 622. We see very good capacity retention there as well. And here you see roughly how we do what we do. We start with a high conductivity sulfide glass ingot that gets pressed in step 2 to form what's known as a preform that goes into our draw tower, which is in Berkeley, California. And then we draw it down to thin glass. That then goes into a PVD system where we deposit the moisture barrier and lithium. So just to kind of blow that up a bit, you can see here, this is actually a sulfide glass preform. We're now making larger preforms, but in any case, that preform is large enough to take into the draw tower. And the tower, as you see there, which obviously is protected from the environment while we're drawing the heated glass. And then there you see, well, in fact, that's the ideal, right, is to pull out thin glass. So if we look at the glass coming out of the draw tower with a confocal microscope, you can see that we very quickly get down to 60 microns, and pulling a little further, we're in fact pulling glass down all the way down to 15 microns thick. That is an ASR about 2 ohm centimeters squared. So, the end goal then is to commercialize the material in a form like this, where we have sulfide glass, very conductive, coated with a thin layer of lithium metal, and then that is used to build next generation batteries. And so each one of these processes, including putting down the lithium, is economic. And so we think ultimately we can get to parity, but of course, you never start there. We will start releasing the product in premium markets. And if you look at just the jump, this is the jump from lithium ion to lithium metal, you can see it's significant. Regardless of which cathode you're using, it's a very significant jump in both gravimetric and volumetric energy density. And so the battery, at least in its first iteration, first commercial form, will look like this. It will be a hybrid. So, it's a solid state electrolyte bonded to lithium, but the cathode will have some liquid in it. So this is kind of a hybrid design. You can see the kind of energy densities we're projecting into. We'll be there soon. And, we'll start, of course, in consumer electronics, drones, medical devices, and ultimately in EV. So I'd be happy to answer any questions, and that I will end my talk right there.
Thank you very much, Stephen, for this interesting talk and for introducing these two different alternatives of solid-state batteries to all of us. We have a couple of questions from the audience. The first one is, in this kind of glassy materials-based lithium metal batteries, what is the ionic conducting component inside the cathode?
Okay, sure. Yeah, I'd be happy to answer that. So as I mentioned, in this first iteration, this is a hybrid design. So although we're using a solid glass electrolyte to enable lithium metal in the anode, the cathode is conventional. So it can be, NMC 622-811, but the electrolyte then is liquid. It's a liquid electrolyte that permeates those pores. So in that sense, it's the first iteration of our design is not technically fully solid state. It's a hybrid. We are working on another design, which in fact uses sulfide glass in the cathode, but that's still in development. As you can imagine, that's, solid state composite cathodes are tricky, but so there's work there, but we'll start with the hybrid design.
Thank you very much, Stephen. And in this kind of glassy materials, the shear modulus of this layer is strong enough to block the growing of lithium dendrites.
That's correct. Yeah. In fact, so I put up one slide showing the measured modulus. We did some work with Eric Herbert and Michigan Tech, and so we did nano indentation of the glass. And these glasses, in fact, are quite strong. So they're strong enough to block dendrites. And as I mentioned, when you get down to these dimensions, they're also quite flexible. So you can use roll-to-roll manufacturing.
And finally, have you worked or have you taken into consideration recycling of these kind of materials?
Recycling, yeah. So I think the glasses, that should be relatively straightforward because in fact, you can dissolve them in water, right? These glasses can be dissolved. So I think the glass itself, that would be relatively straightforward. As you probably know, if you dissolve these materials, you will get H2S, but that can be converted immediately to Li2S, which is one of the basic materials that goes into these glasses. So I think that part is simple. The cathode, recycling of the cathode will look very much the way it's done for lithium ion. So there'll be some moderation or modifications to the recycling process, but yeah, I think it can be done.
And there is another question from Mark. Do you need any pressure inside the cell in order?
Yeah, it's a good question. So we do not have pressure on the cell. However, when we go to extended cycling and we have multi-layer stacks, it's possible that there will be an effect of pressure that it may it may assist long-term cycling. But for the time being, all of our testing is done with very effectively light spring pressure. So we don't compress the cell. It's very different than, say, the Toyota approach, where they have composite cathodes that really require tremendous compression to keep the solid-solid interfaces in touch. So we don't do that.
Okay, we have some other questions, but unfortunately we don't have time to answer all of them in live. We'll take note of all of them and we'll answer them in writing. So now we can move to the next question, to the next talk.
Yes, we are going to talk now about market trends by the hand of Xiaoxin He, Principal Technology Analyst of IDTechs. The title of her talk is Technology and Market Trends of Solid-State Batteries. Let me introduce her, Dr. Xiaoxin He. Since joining in 2014, IDTechs has been conducting technology scouting and benchmarking, doing market research and analysis, providing player assessment and evaluation, and offering business insight and opinions on emerging technologies. Xiaoxin has helped multiple customers to understand their technology capabilities for existing and various emerging markets, as well as to find out potential commercial opportunity and strategies. Let's see this interesting talk.
Hello, everyone. It's my great pleasure to be here. And today my presentation title is Technology and Market Trends of Solid-State Batteries. My name is Xiaoxi. I'm Principal Technology Analyst at IDTechs. In the company, I'm leading energy storage research, and for myself, I mainly focus on emerging battery technologies. Before we start, I just want to have a few words about our company. IDTechs is a market and technology research company focusing mainly on emerging technologies. As you can see here, energy storage is just one of the technologies we cover, but we also include other technologies and their potential applications. So I think I don't need to emphasize the importance of solid-state battery and how much interest that we have received so far from both academia and the industry. But from this worldwide battery target roadmap, I just want to emphasize several programs, including the Battery 500 in the US, Made in China 2025, and Horizon 2nd in Japan, not to say the Integrated Strategic Energy Technology Plan in Europe. So as you can see, and on the right-hand side, all solid-state battery technologies is just one of the several that being discussed. So if we look at the different technologies, they have different future trends. So battery usage is really application dependent. So here we mainly focus on lithium-ion batteries initially, and especially electric vehicle applications. So now you can see from state of the art of what we have most often, we gradually move to high nickel version like NMC 811, NCMA, cathode materials. We also have silicon anode, and so the composite anode. And there is another direction, which is to go to solid-state batteries, including both the polymer and the inorganic choices. So, of course, lithium metal anode is one of a very important component as well. So here, those technologies, they are not exclusive to each other. So that means a solid-state battery could go with a silicon anode or lithium metal anode. So actually, lithium metal anode is a really important component for future solid-state batteries. So here we show you this table with the most common solid-state electrolyte and their densities with a comparison to the liquid counterpart. So as you can see, most of the solid-state electrolyte, they have a density higher than the liquid electrolyte. So that means if you just replace the liquid electrolyte with the other electrode unchanged, you may not necessarily have the benefit of the higher energy density. So we did a calculation with NMC811 cathode and a 40 micrometer electrolyte. And then you can see the result showing on the right hand side just for LL0, the garnet one. So you may say if we just use the graphite anode, but with the solid state electrolyte, then the both the volumetric and the specific energy density, they actually have a drop compared with the lithium-ion batteries. So even when you replace the graphite anode with lithium metal, you can still see a slightly drop for the specific energy. And so that is for the case of the LLCO. And because the density is really high, so the target thickness should be still smaller than 40 micrometer in order to really get a benefit in terms of energy density. So in the future, lithium metal will make a difference for the cell. So that is a really important trend. We can also see the anode-less choices. So that means the lithium metal anode is electroplated during the charging state. So that means you don't need to manufacture the lithium metal anode initially. So that could necessarily reduce the cost, material cost, and also manufacturing cost. So of course, that approach would be a little bit more difficult. So there are also several companies targeting this approach, such as QuantumScape and Samsung. So just focusing on the cell wouldn't be sufficient because in the future, and also like even nowadays, lots of players, they gradually realize the importance to work beyond just the cell. So even for lithium-ion batteries, we can see there are lots of change to move from cell to the pack set. So that means they wouldn't have modules in between, but just to have cells arranged to form a pack. So by doing that, they could reduce the volume and weight in order to increase the energy density. So here you can see there are several different business models for how the automotive OEMs could work with battery manufacturers. So depending on who work on what, that will decide who will capture the value. So in addition, that will also change the standardization as well as maintenance and the repair. That will also make an impact on the supply and the purchase, etc. But in terms of the battery module or pack, both for lithium-ion batteries and solid-state batteries, so we have some necessary components. For instance, all the cells, they are either connected in series or in parallel in order to achieve final configuration in the pack. And there are foam pads which will allow the cell to swell. We need structural members such as the end plates, tension members, so they can control the cell to swell and also make sure all the cells they can retain in the battery pack. The thermal management systems, they are used for the cell heat control. And we also have thermal barriers, which is used to prevent the thermal propagation. So a very, very important question between the solid-state battery and lithium-ion battery is because of their different performance. So the different pack requirement will also be different. So for instance, most of the solid-state battery may need some external pressure, and we are not quite sure about this compression force. What is the correlation with the state of charge and aging processes? So that means maybe in the future, the structure members of the foam pads probably need to be added in order to cooperate this change. So in addition, because a solid-state battery, they are more tolerant to overcharging and over discharging. So that means probably it's possible to eliminate the redundant cell voltage sensing and also other sensing components for the cell health. So in terms of the thermal management system, so many people, they talk about the reduction of thermal management system, but it is probably more of the question what temperature range to make sure the solid-state battery to work within. In terms of the thermal barriers, it is possible to remove some of the thermal barriers because the solid-state battery usually has a better performance. So in terms of the cell and the pack, there needs to have lots of changes. So coming to the commercial area, so we always ask a question, where is a solid-state battery? So from this technology readiness level, we would say most of the startup companies and also some battery companies who have divisions to work on solid-state battery, they are mainly in the technology development stage and maybe early pilot and scale-up stage. So from this image, you can see from basic research and development to mass production, it usually takes several years. Most of the companies working on solid-state battery, they are mainly in the sample line, R&D stage, and test pilot line. So that is why we wouldn't expect a mass production to happen before 2025. So in terms of the cell manufacturing, there are lots of options. I think a really important consideration is the compatibility to existing facilities, because that will affect the cost and the complexity. So for instance, the cathode material usually that involved with the cathode and handling of lithium metal. So both of the procedures will add a complexity and make some challenges compared with lithium-ion processes. So in addition, because we probably don't really need the formation and the aging processes for the solid-state batteries, so some of the manufacturing procedures could be reduced or even omitted. But from the lab to fab and also to mass production, there are lots of details we need to consider. So cost reduction, yield improvement, and quality control, so they are also important factors. And you can see there are different choices in terms of the technology and the procedures, because they are really technology and chemistry dependent. So for instance, you may need a really high temperature for the sintering process for oxide electrolyte, while for sulfide-based electrolyte, and so inner gas conditions may need to be applied. So that is why we think it's really important to give an analysis about the different technologies. If we look at the different value propositions of solid-state battery, we really talk a lot about the energy density. So because of the possibility to use lithium metal anode and also high voltage cathode. So of course, safety is a really attractive factor because we don't really use flammable organic electrolyte. Although for organic solid-state batteries, it may not be the case. The safety could be improved, but there are still some flammable components remain. Because the eliminating capacity loss process, it is possible to increase the cycle life. And of course, people may talk about the potential low cost because of some of the components could be reduced or removed. And the flexible design is also a really important consideration. So both for non-electric vehicle, like consumer electronic applications, but also their flexible design, and both in series and in parallel. But in the meantime, there are also lots of challenges. For instance, if we just replace the electrolyte, as we discussed before, it's not necessary to give us a better energy density. And most of the solid-state batteries, because the higher internal resistance and the worse interfacial compatibility, and the charging speed could be difficult to improve. Although we can see some players, they demonstrated 80% capacity after 15 minutes charge. In terms of manufacturing, there are some procedures which could be omitted, but on the other hand, that may involve with the higher cost solid-state electrolyte manufacturing procedures and also other specific conditions. So not to say there are some other handling issues and cost issues. So definitely in the initial stage, the cost would be higher compared with lithium-ion counterpart. So there are different technologies which could be characterized into inorganic solid-state electrolyte and organic solid-state electrolyte. So we have 8 different groups of inorganic solid-state electrolyte, and there is a comparison of different factors. But the key message is there is no winning technology overall. But when we talk about the technologies in general, we group them into 3 different big categories. That is polymers, oxide-based, and sulfide-based electrolytes. And here you can see the radar chart to compare the different performance and parameters. So in general, polymer-based electrolyte, they are easier to make and fabricate, and that is also the one closest to commercialization because there are already some vehicles equipped with polymer-based electrolyte, but they have a low antioxidation potential, higher operating temperature, lower ionic conductivity, etc. For oxide, usually has a really good chemical stability, but the higher centering temperature will make the manufacturing more difficult, not to say the higher interfacial resistance. Sulfide-based electrolyte usually considered to be the ultimate solution because of the higher ionic conductivity, but in terms of manufacturing, there are also some difficulties. So here you can see lots of players working in the solid-state battery area globally. Although some of the players, they abandoned the technologies, others, they gradually move to alternative technologies. There are also some companies, for instance, they move from sulfide-based to oxide-based. But in general, we can see lots of players in the areas of there are lots of recent activities with the different companies. But the general message in this area is we can see a growing number of collaborations, partnerships, and joint ventures. And the major targeting application is electric vehicles, although other applications may become easier to be realized. So here we can see the key takeaways include the technology trend challenges and also market trends. So because this is a really short presentation, and if you are interested in more details, we have a report in this topic, and I'm also happy to have some questions to discuss with you. Thank you so much.
Thank you very much, Xiaoxi, for this comprehensive view around the solid-state batteries technology. In your opinion, how the most likely business model around this technology could be? I mean, who will dominate the solid-state battery commercialization? Will it be current lithium-ion battery makers? Will they be startups? Will it be a collaboration or a partnership between automotive manufacturers and these small startups? What is your opinion about this?
Thank you so much for your question. So basically, there are lots of efforts from startups and also teams in conventional battery makers, and also investment from automotive OEMs. But gradually, we can see a increasing number of partnerships, M&A, and so I would say the automotive OEMs definitely play an important role, especially for electric vehicle applications. But apparently, they also will work with the battery companies. So I think this technology is not just about the cell. So that means we will need a collaboration from both parties, and of course with other companies in the supply chain to get involved in.
Thank you very much again, CIC, for taking part in this webinar. And if there are no further questions, we can move to the next talk.
Yeah, thank you so much.
Okay, so happy to introduce our next speaker, who is my colleague, Roberto Pacios. So Dr. Roberto Pacios is the Technology Coordinator of the Electrochemical Energy Storage area at CIC energiGUNE, as well as the responsible for the research group on cell prototyping and postmortem analysis and battery aging. He has had experience in several fields, including microelectronics, photovoltaics, and energy storage, and he has coordinated several national and European research and technology projects. He also has a strong experience on transferring newly developed technologies to industrial products and services supported by private and public funding. Roberto is going to talk us about innovative manufacturing routes for next generation batteries in Europe. Roberto.
Good afternoon, everyone. My name is Roberto Pacios from CIC energiGUNE, and I'm going to talk about the competitive production of solid-state batteries, how the production of these batteries should be if they really want to achieve commercialization. But before starting, let me very briefly introduce you the IMAGE European project that has economically supported this activity. This project has the goal of somehow pushing the European lithium battery industry, in this case by looking and studying the necessary assembly and manufacturing processes. You can find more details in the webpage of the project. And now, yes, solid-state batteries are still seen today as the holy grail of electrochemical energy storage devices for which all the desires in terms of market indicators can be fulfilled at once. High energy and power densities, long operational lifetimes, low cost, and no issues related to safety is the most recurring dream for battery manufacturers that could become a reality with the manufacturing of solid-state batteries. In short, when we talk about solid-state batteries, we refer to the possibility of replacing the flammable liquid electrolyte of standard lithium-ion batteries by thin solid films that also enable the use of high specific capacity anodes as lithiums. Thanks to this, we can expect a better performance in terms of mainly rate capability, energy density, and security. But the reality is somehow different, and up to date, at least, I'm not aware of any commercially available device with this technology that outperforms the standard lithium-ion batteries that we can find today. We'll see what the future brings. It is true that the development is still in a very early stage, but in any case, any competing technology will have to be evaluated or benchmarked against existing ones in terms of performance, what we said before, manufacture, and scalability to fulfill market demand and price. So far, the fabrication of this kind of devices is the most limiting factor since performance and cost is being supported by the very active research and development on novel materials with better and better electronic and processing properties. In contrast, it doesn't exist an industrial manufacturing technique able to produce the gigawatts that we would need for either mobile or stationary applications. I don't want to get into too much detail with this. The important issue here is that it doesn't really matter what the electrode is made of. Every material has its positive and negative features, but the fabrication process has to be somehow consistent and independent of the kind of material. And how this process has to be? Well, that is what I'm going to talk about today. These are some of the properties or features that the process has to show if we want to fulfill the expected demand of batteries in the coming years, especially if we refer to the electric vehicle. And of course, at a very competitive cost and sustainable, not only environmentally, but also from the social point of view. And I'm referring to raw materials mining and extractions, and also to the working condition of employees along the full value chains. Taking all these issues into account, will give us the roadmap for competitive manufacturing of the battery of the future. This is the methodology we have used in order to get to that point. First, a review of all potential manufacturing techniques that would be used for the fabrication of electrodes and electrolytes. Not only techniques that are being used today, but also other fabrication techniques that are being used in other fields that could in principle be also transferred to the battery world. Then, we will apply a first filter attending to material, product and production requirements. This is how the process should be from these 3 points of view, what we would like or what we do expect. This will give us a fair picture. Then we will define some additional features that could or should be improved for the resultant techniques from the previous step. And finally, we will be ready to validate and verification against legislation and regulations. So let's get started. This is the initial list we have considered depending on the medium to process the active material: liquid, vapor, something in the middle like aerosol, and solid or solvent free. Here, in this very nice publication, you have all the details and also the industrial field of application they stem from. The next step is the most important one. What kind of restrictions and or limitation we fixed from the material, product and production point of view. The selected process in this way doesn't have to affect the stability of either the active material or the substrate. It has to be able to produce thin films of a given thickness uniformly across relatively large areas with low error rate and high reproducibility. And finally, the process has to be safe and sustainable in terms of what we told before. If we apply these filters, we can rule out a large number of them and focus on the remaining ones. If we deepen in these remaining ones, we can somehow order or prioritize them as a function of the requirements we had previously defined. First, we plot the ones that we have already discarded to have them also as a reference. And from here, we can suggest 3 different parallel or even complementary approaches. First is wet or solution processing with some drawbacks regarding mainly safety and environmental impact. We'll see how to solve them that later. Aerosol coating with more or less the same drawbacks as wet processing. And extrusion, which is one of the most promising attending to this criteria. These 3 approaches are summarized here. Aerosol coating is also somehow penalized by the very low TRLs. It's very incipient, and extrusion is supported specifically because it's solvent-free. How can we improve this? What else can we demand in order to distinguish between them? The fine-tuning we talked at the beginning. It would be very appealing if the process was roll-to-roll compatible. I'm not saying that extrusion it isn't, but with wet coating would be considerably easier and I would say also faster. And finally, if we are using solvents, we should try to use those that have been proved as innocuous from the human and also from the environment. Here you have some of them, and eventually water. At the anode, the situation is very similar, but I didn't want to include it in the analysis because in theory, you always have the possibility to start from lithium foil without minding how this lithium foil is processed from the ingot. So in summary, even in the short term, we can already exclude some of the potential manufacturing techniques according to material, product and production requirements and focus on 3 alternatives. Co-extrusion is a very promising approach for the mid and long term since it doesn't make use of solvents, while for wet and aerosol spraying, we would need additional developments to make active materials soluble or dispersible in green solvents and eventually water. I put active material functionalization here and here, but it's very important to remind that it's exactly the active material functionalization what enables wet coating. Nowadays, most of the efforts are focused on making oxide and sulfide electrolytes soluble or dispersible on organic solvents in order to be able to wet process them. At the anode level, lithium metal will be, without a shadow of a doubt, the preferred material in the short and mid-term, mostly processed from solid phase from the ingot, mainly extrusion and lamination, but it's also very promising the electrochemical deposition of lithium thin films from the ingot, and even the so-called anode-free approach with the in situ electrochemical lithium plating during the first formation cycles of the battery cell. Other approaches, as wet coating, will perhaps be possible, providing the development of new alloys or composite other than lithium with also large specific capacities. And last but not least, something very important I don't want to forget is that there will be not a definitive manufacturing technique. There might be more than one, and this can even be driven by application. Here you have some market application for which solid-state batteries can find commercialization. Their adoption is more likely to start with applications that don't require much energy and can therefore be relatively small, and also to take into account that some of the features cannot be very relevant for some applications but be very important for others. Cost and power density can, for example, not be the defining criteria for medical implants, but be very important for stationary and automotive. This will define, up to a certain extent, the manufacturing technique. It's in this way perfectly possible to fabricate small devices by vapor deposition, as ILICA, for example, is doing, but considering wet processing for larger area devices, as ILICA is also doing. And I didn't want to finish without looking at what the main players in the field of battery manufacturing are doing nowadays. This is a small compilation which also somehow validates the roadmap we have presented, since, as you see here, most of the players are already considering wet processing. So this is all from my side. Thank you very much for your kind attention, and if you have any question, I will be glad to at least try to answer them. Thank you very much.
Thank you, Roberto. Very detailed overview about the solid-state batteries manufacturing options. I have a question for you. From a manufacturing point of view, essentially, which is, in your opinion, the solid-state batteries technology that will strongly, successfully enter in the market in the near future, just taking into account the manufacturability?
It's a very good question, and at the same time, a very difficult question to answer. Is the $1 million question. If anyone knew, it would be probably millionaire the next day. It's very difficult to answer, but I would guess that we have, or somehow find the balance between the processing properties of materials and the electrochemical performance of these materials. And in my opinion, I think a choice that is very well positioned in these two things is the composite polymer electrolytes, in which polymers are blended with some ceramic load. Because in this way, you can take advantage of the processing feasibility of wet processing thanks to the polymer, and you can also get benefit from the electrochemical performance of solid electrolytes. So that would be where I would put my money on.
Okay, thank you. Thank you very much, Roberto. Next stall deals with the Battery 2030 Plus initiative. The title is Technology Road Mapping Towards European R&D Ecosystem, and the next speaker is Professor Christina Edström. Let me introduce her. Professor Edström coordinates the EU Large-Scale Research Initiative Battery 2030 Plus CSA and the Armstrong Advanced Battery Center. She is Professor of Inorganic Chemistry at Uppsala University. Her research comprises studies of lithium-ion batteries, but also new battery chemistries and systems. She is a member of the Royal Swedish Academy of Engineering Science, honorary doctor at the Norwegian University of Science and Technology, and in 2018, she received the Grand Prize from the Royal Institute of Technology, KTH. She is, since 2019, a Wellberben Scholar. Professor Christina Edström is today Professor of the Inorganic Chemistry at the Uppsala University and the Battery 2030 Plus Initiative Coordinator. Sure, this will be a very interesting talk.
Hello, I'm Kristina Edström. I'm professor of chemistry at Uppsala University in Sweden, and I'm very grateful to the organizers allowing me to talk about the large-scale research initiative Battery 2030 Plus, technology road mapping towards European R&D ecosystem. And we are a large initiative which aims at reinventing the ways we invent the batteries of the future. So the roadmap I will present to you is slightly different from the classical roadmaps where you look at different chemistries and when they are coming in time for certain applications. In particular, we see around the globe roadmaps for batteries targeted specifically for the transport sector. And my deputy for this large-scale initiative is Dr. Simon Perrault from CIC in France. So why a large-scale pan-European project? Well, the European Commission realized already about 4 or 5 years ago that we really need to work for a climate-neutral society, which is called Green Deal, and today it's even called Fit for 55 to 2030, which means that we need to reduce the carbon emissions with 55% to 2030. And that batteries would be a key technology. But they also saw that if we are really to have this transformation, we need to have more of initiatives around batteries. We need to produce batteries also in Europe, because if you look at 2018, we had a little bit of the share, the global share, but the majority of the production is in Asia, and it still is. And since 2017, when they launched both European Battery Alliance and started to say that we need a flagship type of long-term research in parallel with the industrialization, which is Battery 2030 Plus today, we have moved up in the number of electric vehicles are increasing a lot, which means also that the battery sales are increasing. And we see that many companies move into Europe, both from Asia, and that new companies are starting up also being European companies. So it's a very interesting development at this moment. So it sort of follows these expectations that were put in place 2019. We are still in that direction. So what the Battery 2030 Plus wants to do is provide breakthrough technologies to European battery industry by thinking a little bit outside the box, thinking new ideas, golden nuggets that could be specific to European industry. And the batteries we target, we call that we go for the ultra high performances, but we are chemistry neutral. I will come back to that. We also target smart functionalities. Can we actually make the batteries really, especially the new battery solutions that are still a little bit unstable and provides more energy content? Could we make them in a smart way with smart functionalities so we can trust their performances? And of course, today you can't do anything without thinking environmental. So by having this long-term vision at low tier levels, but always having the industry in mind, so putting a realistic framework on what we are doing, we hope that we can contribute with skilled people and long-term leadership in both markets and research in this respect. So who are we? Today we are 102 partners distributed over 24 countries. And we have formed 7 projects. I am leading the coordination support action, which is trying to put all these projects and organizations into working together, which is really, really important. And we are in our starting configuration, which is a 3-year period. And as flagships traditionally during Horizon 2020 expected to be 10 years, we are also aiming for a 10-year, at least 10-year perspective. So I can tell you already now that we are in the next framework program, which opens next year to continue after our first 3-year period, which is very positive. Then we have actually projects that are carrying out the content. And I will give you a little bit flavor of what we can find in these projects. The largest one is called a big map. It's coordinated by D2. And we have 3 about sensors, and we have 2 about self-healing capabilities. I'll show you a little bit more. And in this coordination support action and supporting organization to this, we have collected some of the largest partners, not all, unfortunately, because funding is too little, spread over Europe. And we have also a number of associations and organizations supporting what we are doing and following and guiding and criticizing everything you need to make this kind of large-scale initiative functioning and working. And we are targeting all kinds of batteries. Of course, the transport sector is the driver, strong driver, the mobility, but we also see that the grid and frequency regulation and large-scale storage comes up more and more, and also discussion of second use of batteries. But we should not forget portable electronics, medical devices, and what's coming up as new application when it comes to batteries. So we think addressing all these applications with transformative ideas instead of incremental research. So by making a roadmap where we actually have a chemistry neutral approach, we want to accelerate the discovery of interfaces and materials and smart functionalities, sensing and self-healing, and always have cross-cutting areas as how would you manufacture and recycle the things that you put up in your ideas and projects that we're now running. So we're going for future chemistry. This means that we also involve, for instance, redox flow batteries and not the ones that typically only for transport sector, and many of the post-lithium battery chemistries where we maybe even need to move the sodium into the more present batteries and the different generations of lithium battery chemistries. And we have put all these ideas that how we should do this, accelerating the discovery into a roadmap. And this roadmap you find on our webpage. And what we are now doing is that we are both implementing and creating and recreating our roadmap. And we hope, of course, that the whole European community will be a feedback source for this. And we support Europe to reach the sustainable goals. We suggest new R&D action, which we are exactly now in the process of doing, and there will be a lot of discussion and openness around this for the 23-24 calls that come out. So that is in the loop currently. So we are in the discussions also and sending in this as suggestion to the European Commission. And of course, we are part of the battery partnership where our calls will be sort of positioned in this landscape. We also develop curricula for education. Skills have come up as one of the really key issues in Europe if we want to have this transformation to electrified society. So what we have built in our roadmap, it's a way of trying to bridge the different projects we have. I mean, we have the different sensing technologies. We have this largest big map with a materials acceleration platform, specific focus on battery interfaces, because there we see a lot of the unwanted side reactions. Is there where we need to have better charge transfer reactions in solid state batteries, better wetting of the lithium metal, etc. Since this is a solid state conference. And we are trying to discover new self-healing materials for batteries, which also might be interesting in the solid state. And actually something to think there, where we have things that, you know, when the lithium metal is cycled, you can get a gap to the electrolyte, the solid electrolyte. Can we have something grabbing that space and sort of filling it like a self-healing component? That could be one idea. I don't know if it's feasible. I'm just making it up as I speak. And then we have feedback loop between these. So they are actually using a lot of the techniques and ideas developed in Big Map to try to use it when it comes to self-healing and sensing. And we have the manufacturability and recyclability also discussed in these project meetings we have between the projects. Oh, sorry. Sensing. So I thought I should give you a little bit flavor of how we work and how we have made our roadmap when it comes to sensing. And the goals we have are divided into 3 sections. It's after 3 years until 2023, and then to 2026, and then to 2030. That's our goals. And for sensing, we have said that we should apply non-invasive multi-sensing approaches, transparent to the battery chemical environment. And the 3 different projects have different approaches. So there are different developments of sensors to really go into some kind of fine-tuned details that you cannot do with today's sensor into the battery cell. Then we have also that we want to integrate these sensors to existing battery components. Here we have learned that it's could be extremely interesting for the recycling purposes, that you can really, through sort of a BMS system and control system, say something about the content and the situation of a certain battery cell. And here we have also different approaches between the SensiBat and the InstaBat project. And then we should have deploy sensors capable of detecting various relevant phenomena. Can you really see with these sensors that you have interface dynamics, for instance? And for this, InstaBat is making a multi-sensor platform, while the SensiBat go for certain properties like pressure, temperature, impedance. And the Spartacus instead measures mechanical, acoustic, thermal, and electrochemical properties. So there are synergies and differences between these projects in a very good way. Similarly, we have goals also for the self-healing, where we wanted to establish a new research community in Europe. Self-healing is something that, since we wrote this roadmap and started to make it public 2018 time and 2019 and discussed, it has become a really, really visible as a concept for batteries. So this is really not the only ones in Europe today doing self-healing work, but these are the targeted projects here. And they have also quite different approaches. For the Bat Forever, they go for silicon with its volume, large volume expansion, and polymeric systems that can break and reform and reshape, and thus sort of try to protect the silicon surface from unwanted reactions with the electrolyte. Hidden goes for what we could say a solid state concept, where they use 2 different ways. They use liquid crystals in liquid electrolyte to break dendrites that are formed on the surface during cycling. And then they have solid piezoelectric separators with the same idea that when the sort of dendrites grow into that separator, it should break it. And if we will be successful, you can listen to the 7th of October when we have our yearly annual meeting, which is open and digital. The Big Map works on developing an artificial intelligence accelerated infrastructure for the European battery community, and you can read more in their webpage. And the vision is to have a neutral platform and to really accelerate closed-loop discovery. So what you do is that you have a lot of experimental high throughput optimizations and reactions from characterization, synthesis, etc. as an input. And then you have a database which is now built up. Some of that will be open source, but there will also be some protected ones. And you try to have an electronic notebook, really keeping track on all experiments and all kind of modeling work that is done, so that you can really make it what's called fair, open, and transparent, and share, that we can share the data. And here, interfaces in interfaces play a critical role in all battery technologies. And this is something that is really targeted as by developing hybrid physics and data-driven models. And here we have lots of new interesting discussions between experimentalists and theoreticians. We just had our annual meeting with 130 people involved, and it was very interesting to see how these really strong experts in Europe from European Modeling Council, we can get good ideas also as experimentalists on this. So this is sort of this loop, what the big map tries to target in this space. Then we operate on characterization of battery interfaces to databases, to computational design of battery materials, and not have it the traditional Edisonian way of starting with a model and then trying to do the compound and then going back to the model and saying that was wrong, you have to redesign it because you can't make the material, etc. But learn from machine learning and learn of all the data we collect and share in this big databases we're putting up. And the goals, if you look at the roadmap, then what we are expected to achieve by 2023 is a shared fair data structure. Just to put that up is a thing in itself. We have just published the largest data management plan that you can find in literature. You can find it published as a scientific paper, and to have simulation, code scales, and experiment, you need to have a common ontology, and we're building that up with something called BAT-Info. And we're also developing and sharing externalizable tools, apps, and autonomous workflows in the Big Map App Store for the battery community. So you can go in on the Big Map website and learn more about this. So just to summarize this, the idea is to put a lot of these platforms in place, and then next phase is to integrate these parts. So in the course that will open 2022 is a continuation of Big Map, but emerging of sensoring and self-healing into one project. And then we also suggest some other things. There will be a specific interface code, for instance, and there will be also some other codes. So in fact, the funding and the portfolio of Battery 2030 Plus will be a bit larger in medium term than it was in the starting phase. And then in long term, we hope to put all these together into some kind of big platform. That's our dream. And the idea is that we need to make the European batteries fit for purpose. So by this, I'd like to thank all the Battery 2030 Plus team and all the projects for this nice work. And I hope also to involve more of you, and we are open to collaboration in many different ways. We do collaborate also with the synchrotron and neutron facilities because they are important. And we also want to collaborate with projects in the other kind of EU schemes that we find, as well as what's going on in both Batteries Europe and in the Battery Partnership. So thank you very much for your attention.
Good afternoon. My name is Michel Larman. I'm going to speak about solid-state batteries from the invention to what is being done nowadays, mostly with different electrolytes. If you speak of need for electrochemical storage, you will need big batteries for automobiles and for load leveling. If you speak about electric automobiles, you're speaking of batteries which are about 50 kilowatt hours. When you speak of load leveling, you're speaking of 1 megawatt hour units, much bigger. If you imagine that you have 1 billion cars on the road and you want to turn 10% electric, you're going to need 20 million tons of batteries. It's even more striking when you speak of grid storage, where if you only store 10% of the electricity per day, you are going to need 60 million ton batteries. So sustainability is a prime criterion. Okay, we have to remember that all elements are born equal. I mean, if you look at the periodic table, as you know, in classical form, I would like to focus on this, the drawing of the periodic table, where the surface is proportional to the abundance of the elements. And as you can see, it varies widely depending on the element. The lithium and the cobalt, which are used in batteries, are in rare supply, limited supply. So you would need to think in terms of iron derivatives and sodium, possibly instead of lithium for batteries. If we think of batteries according to chronology, batteries started to be lithium polymer batteries with an intercalation anode and a metallic lithium. They are solid-state batteries working because the electrolyte needs to be warmed up to become conductive enough to 60 degrees, above 60 degrees. Then came the lithium-ion batteries after 1991, where the liquid electrolyte is used between two intercalation electrodes, graphite and something like NMC, and the temperature of operation is between minus 20 and 55 degrees, where you start to have safety problems. And what is the future of batteries? Certainly to try to work with their alloys or metallic lithium and more capacity intercalation compound. The future electrolyte is going to be polymer, ceramic, composite, or ionic liquid. I will be speaking about ceramic and polymers. We could say that arguably the electrolyte is the most important component of a battery. In fact, if you speak of systems using liquid electrolytes, which are the majority now, you have got conventional organic solvents like carbonate and with LiPF6 as a solute, or ionic liquids. If you speak of solid electrolytes, you have got the choice between ceramic and polymers. The ceramics can be divided between glassy and crystalline materials, and polymers can be mostly divided between polyethers, the archetype being PO, or polyesters, archetype being polypropylene carbonate or polycaprolactone. In between, if you combine ceramic and polymers, hoping to have the best of new worlds, you have composites, which are high in the priority list of scientists at the present time. And the problem with polymer electrolyte is that polyesters are not stable versus lithium metal or sodium metal, and polyethers tend to have a low conductivity at room temperature and a low transport number. The fraction of the current which is carried by lithium is less than unity, close to about 20%, which is a disadvantage, as I will show. In fact, there's only in the batteries with polymer electrolytes, which are commercial, of course, in addition to the conventional organic solvents, which represent 99.5% of the batteries made. Ceramic electrolyte can be garnet type, like the LLZO, which is zirconium, lanthanum, lithium oxide. And you have sulfide derived from LiPS4, which is Li6PS5Cl, like argyrodite. And the conductivity at room temperature of this electrolyte is quite high, between 10 to minus 4 and 10 to minus 3, possibly reaching 10 to minus 2 at room temperature, as I say. The problem with LLZO is that they are not very resistant to dendrites, the needle type formation from the negative electrode on recharge, which can pierce the electrolyte and make a short circuit. If you make a test between lithium metal sandwiching zirconium garnet, you can see that immediately, after a couple of hours of operation, your garnet type is like blue cheese, and the blue veins are in fact metallic lithium, as can be shown by the NMR, solid state NMR. You have lithium which has been growing inside the ceramic at the grain boundaries. With the argyrodite, you have got a different situation. The compound is highly conductive, as you can see on the red curve, and you can build a battery with an MMC cathode, high voltage cathode, a solid electrolyte which is argyrodite, and instead of lithium electrode, you have a silver carbon composite, which allows to deposit a silver lithium alloy close to the voltage of lithium metal. And this works extremely well. As you can see, a battery can cycle for 1,000 cycles with excellent Coulombic efficiency. And this is considered as a breakthrough, probably the best that can be made in solid-state batteries for room temperature operation. And this material, the argyrodite and the sulfide in general, are easy to press into dense membrane. But they tend to be extremely sensitive to moisture and release H2S, which is highly toxic. So there is an advantage and a drawback. Polymer electrolytes, on the other hand, have their archetype with polyethylene oxide, which is highly solvating, or you have polycarbonates, polypropylene carbonate, or polycaprolactone, which is a polyester. And these compounds have got conductivities 10 to minus 4, 10 to minus 3, only above when reaching 70 degrees to activate the motion of the polymer chain. And the conductivity at room temperature is closer to 10 to minus 5, 10 to minus 6, so not usable for practical operation. A solid-state system is not a view of the mind. In fact, there was cars on the program called Autolib, 4,000 cars on a pay-and-ride basis in Paris between 2010 and 2019. And these cars had a 250 kilometers driving range, a 0 charge rate. And also the buses made electric with polymer batteries, which are running in the streets of Paris and Melbourne now. Safety again, I showed you the car which are running in Paris, and we have vandals there. They set cars on fire for fun after being inebriated by alcohol on a Saturday night, and they set fire to Bolloré electric cars, and they burn effectively. And what is absolutely impressive is that the battery is intact after the car has been burned. In fact, the battery can be recycled and reused in a new body of a car. If you want to improve on this situation, try to decrease the operating temperature. You need to increase the conductivity at lower temperature. You need to increase the fraction of the current which is carried by the cation lithium what I call T plus transport number, and you need to keep the processability. For this, we thought of using compolymers to increase the conductivity, and the idea is to take a sturdy CC backbone polymer that would be resistant mechanically to oxidation and reduction are going to be present in the battery operation, to which you attach a flexible tether, which is in this case PPO, polypropylene oxide, and then at the end of the tether you attach another link of polyethylene oxide, a PO-based material, and then this would be able to solvate salts, lithium salt or sodium salt, and this would be able to move freely because of the flexibility of the tether, and you have the sturdiness of the CC backbone. This has been realized very easily, starting from maleic anhydride coethylene as a CC backbone, gefamine reacting this oxygen onto the NH2, and making a polymer with the backbone, a PPO flexible tether, and the PO chain length in which you dissolve the salt, and in which we can obtain the material under entangled chains, which would be a gel electrolyte with good mechanical properties, or a flowable liquid with untangled chains, which can be used to make good contact with the electrode. And the conductivity of these materials is superior to that of PO at all temperature. As you can see, the red arrow, these materials are more conductive than PO at all temperatures. And in fact, this allows to build batteries. If you build a lithium metal solid polymer electrolyte, either PO that we want to compare with our gefamine polymer and with a phosphate, lithium iron phosphate electrode. If you have got a conventional PO LiFSI battery, you cannot cycle the battery below 50 degrees. There is no cycling possible. Of course, if you cool down, you don't operate the battery and warm it up, you can, when you reach 70 degrees again, the battery is not degraded and can operate. If you use a gefamine polymer, as you can see, even if you cool down the temperature, you lose in capacity, but the battery is still operative down to 25 degrees, though of a low fraction of utilization. But this means that it is not hopeless to think that polymer battery could work at close to room temperature, possibly 50 degrees. Let's go to the second part of the polymer, grafting anions onto the nanoparticles. As I said, the transport number is a problem because you have got in polymer electrolyte the dual motion of the anions and lithium, and the anion move 2 times faster than the lithium, so the transport number is close to 0.2, 0.3. So what happens, because your electrodes are only using lithium at the interface, exchanging lithium at the interface, you are going to build a concentration gradient of your salt in your battery when you operate it, and this concentration gradient grows until you have got another concentration and conductivity drops on one electrode, and you have got depletion of salt on the other electrode, and your conductivity drop also. And even worse, what you're doing when you have got concentration gradient and depletion of salt at the interface is the possibility of dendrites growing. This is obtained when the sand time, which is a parameter in electrodynamics, reaches 0. You start to grow dendrites. For solving this problem, we'll imagine to take a nanoparticle to graft the negative charge of the salt onto it, grab some PO chain to make it more compatible, and immerse these nanoparticles into a PO matrix. And then, as you can see, you obtain very nice mechanically sturdy membranes, and which can conduct quite well lithium. In this case, the conductivity is due only to lithium, which can be the only mobile species. And as you can see, the LFP lithium battery cycles quite well with the nanoparticles with a membrane of 50 microns. Okay, let's go to the second action we take onto improving polymer electrolyte is modifying the salt. Usually the salt that is being used, the solute which is used in polymer electrolyte, have shown that you can tether the salt, but if you use a discrete salt, this salt is likely to be TFSI, a CF3SO2N SO2 CF3. And we imagine to replace part of this fluorine atom by protons, starting from 6 down to 3 proton being added, being replaced in the material. And this we would imagine could create hydrogen bonds of the salt with itself or with the polymer, and that the transport number, which is only 0.3 for plain TFSI, would become much higher, which is the case. And as you can see, these new salts have got transport number which are markedly higher than those of plain TFSI. And why is it important? Because the sand time, the time before you deplete your salt and you start dendrites growing, is proportional to the square of the transport number. So every time you gain in transport number, you can gain in current or cycle life of your battery. Let's emphasize on this salt with one proton replaced that we call DF-TFSI, difluoro-trifluorosulfonimide. And let's look at the favorable properties of this salt back to this DF-TFSI for all the salts I've shown in the previous slide. So the DF-TFSI with one proton replaced is in fact very prone to give a very good SEI. If you make a lithium with a PO membrane and cycle it, as you can see, if you have got TFSI, you only cycle lithium for 200 hours. But you can go to 600 hours if you have got a PO LIDF-TFSI membrane. You get more than 3 times longer lifetime with this salt. And it's even more apparent when you use DME to be able to see the surface of your lithium. You can see that the liquid after 1000 cycles still works, and while the TFSI and liquid electrolyte grows dendrites, goes to short circuit within less than 50 hours. And effectively, if you plate lithium onto copper using DME because you want to be able to see this lithium, as you can see with LiTFSI, it is quite dendritic and discolored, and you can see the porosity of the dendrite. And if you plate lithium from DF-TFSI, you can see a shiny, smooth membrane of lithium which has been deposited. And so the SEI that this salt gives is far preferable to that obtained with conventional LiTFSI. Let's try to see if the SEI can be used in a battery other than LFP. Lithium-sulfur battery, are they the ultimate? Sulfur has got a very high capacity of 2000 milliamp hours per gram, and the sulfur is abundant, of course. This is the advantage. The disadvantage is that sulfur and Li2S are total insulators. And the polysulfide in between sulfur and Li2S are soluble in polymers or in liquid electrolyte and make a deleterious shuttle effect. And in fact, we can say that in the absence of a lithium SEI on the surface of lithium, we cannot expect to cycle very well a battery, a lithium sulfur battery. And in fact, this was proven with LiDF-TFSI sulfur battery without taking any precaution. As you can see, a Coulombic efficiency could be kept for 1,000 cycles. The capacity was decaying, of course, but I mean, close to 1,400 cycles were obtained without any bad event on the curve of the cycle curve. This is, to our knowledge, the best result of a lithium sulfur battery cycling without resorting to exotic electrolyte except for the new salt, without resorting to nanocarbon to trap the polysulfide. Simply the SEI of PO LiDFSI was sufficient. And as you can see, the C rate, the power of the battery was still acceptable despite this SEI on the lithium. And I will go to conclusion now. Ceramic electrolyte reach the conductivity for room temperature operation. This is the base, especially the sulfide are the best conductor that one can imagine, possibly better than liquid. LLZO, the garnet, have got a bleak outlook. They are sensitive to dendrite. They have a very high interfacial impedance. So it's not very nice, not very promising. Argyrodite, I mean the sulfide ceramic, are easy and work very well for small surfaces. But I mean, how are you going to make 10 by 20 centimeters of a brittle ceramic? This is a problem to solve, possibly by mixing them with polymers. Possibly, we have reached the upper limit of polymer electrolyte in terms of conductivity with a strategy I showed of tethering the PO segment to a tether itself attached to the backbone to increase the kinetics. With this tethered PO, a 50 degrees operation is possible without any problem. As I said, it can go possibly to 25. The polyester polycarbonate, I did not show any slide for because of shortness of time, do not pass the lithium compatibility test. So this would be solved possibly with dual electrolyte, having a layer of PO on one side, on the lithium side, and the polycarbonate on the positive electrode side. It is still possible to design new salts, and we are focused on high T+, T+ equal 1 for the grafted nanoceramic, T+ equal 0.4 for the hydrogen bonded anions. And with one of the hydrogen bonded anions, we have shown that the SEI building properties are extraordinary. At this point, I want to thank you for your attention.
Thank you very much, Michel. It's always a great pleasure to listen to you. I'm going to start by cheating a bit, and I'm going to ask you the same question as Raquel asked me some time ago. If you had to place a bet, where would your money go? What kind of solid electrolyte will win the race, in your opinion?
I mean, it's going to be a tight race between sulfides like the one I showed, which are multi-grain ceramics, which are pressed, possibly bound with a polymer to make a composite, or polymer electrolytes for the ease of processing. So I think clearly between composites and pure polymers. And of course, the thin film glasses that Steve Visco showed have extraordinary promise, but not for a totally solid-state system as is disclosed.
Thank you very much, Michel. And we have another $1 million question from the audience. What do you think is the most probable reason for the dendrite growth in materials such as this we were talking before, based on lithium, lanthanum, zirconium oxide, garnet oxides?
Okay, I mean, this is definitely due to grain boundaries. You have a ceramic and you sinter them and you have got grain boundaries, and you can have direct injection by electron tunneling into the bulk of the ceramic, and then you start your blue cheese effect.
Okay, thank you very much, Michel. If we don't have any further question, we can close the session right there.
Yes, it is. Before I close this webinar of Image Project, I would like to thank once again to all of our speakers for the very interesting contributions, and also to all of participants to share with us this afternoon webinar. Thank you to all of you. Hope this meeting, this webinar has been interesting for you. And we can now officially close the webinar. Thank you, everybody.